welcome to another live episode of Coding Rainbow. I believe this is episode number 52. I'm here this morning live from the School for Poetic Computation. It's completely empty here this morning. I'm the only person here. I don't know, maybe they're on a field trip or something. So, and today's session will be all entirely about genetic algorithms. I've been talking about doing a session about this topic for a while. I have resources in various areas. But I'm ready to do that today. Now, I have to go through some just sort of scheduling logistics stuff first. Let me just say that if you're watching this as an archive video on YouTube, you can check this video's description and there'll be a link, various time codes as to where the actual tutorial portions happen. In addition, I expect this is going to be about 3 hours long. It's a 10:30. I have till 1:30. I will take maybe a break or two in this live session, but what will happen is I will edit out of this 3-hour session probably 4, 5, or 6 shorter 10 to 20-minute videos, and those you'll find in a genetic algorithms playlist that will also be linked in this video's description. Now, I have a new soundboard system.
Coding rainbow.
I can turn on music. I can turn off music. As always, I always forget. We've got the this dot song. This dot. I'm gonna do this dot. I'm gonna do this. Just nope. Oh, I have that sound effect, and then I made this. This dot song. Just a little snippet there for whenever I forget to put in JavaScript. This dot song. So I'm kind of, are you hearing those sound effects? I hope you are, otherwise that was a really big waste of time. A lot of people have been asking about, I've been requesting that I make a video about my recording setup here, how it all works, and I am definitely planning to do that soon. I'll probably just do that as a kind of record it from my phone type thing. I've got too many screens now. What I really need still is a big screen up there that shows what I'm typing, because right now when I type, I tend to look like this, which means I'm not connecting with you, the viewer. Okay, a 360 video, that's a great idea. I should definitely try to get my hands on a good 360 camera. What other sound effects do I have? I don't remember what this one is. Oh yeah. How's the volume of the sound effects relative to my voice? Let me know how that is. Okay, so a few things that I'll mention, just in terms of kind of promotional whatever stuff. My name is Dan Schiffman. I live here in New York City. I teach at a program called ITP. However, I am doing a residency at this school called the School for Poetic Computation. And part of that residency is setting up a video recording studio, making video tutorials. I'm in the process of inviting guests and other folks to come and make some videos as well. That's something that you have to look forward to, perhaps coming in August. If you are interested in more information about what it is I'm doing, you can go to codingrainbow.com. I actually need to do some work on this website because there's a lot more things that I've started adding that aren't added on the website. But probably the two important ways that you can support my channel are just simply subscribing on YouTube. You'll get notifications whenever there's a new video. You can also become a patron, which is a crowdfunding website called Patreon that I'm using, and I have a Slack channel for subscribers to that where I answer questions and discuss topics and that sort of thing. I'll also mention that if you want to know when I'm doing live streams, you can put your email in here to sign up for email notifications. I sent one out last night about this morning's live stream. And then the other thing I'll mention is that there's 1 week left for, I think, these t-shirts that this t-shirt company called Cotton Bureau helped me create. And so there are green and turquoise and pink and purple, and there are also kid sizes and onesies and all sorts of things you can get. So if you're interested in that, look for the links in the video description, et cetera, on cottonbureau.com, that sort of thing. Ooh, you're having a thunderstorm in Germany. Okay, so that's my quick, I'm getting better at this spiel. We are 5 minutes into this live stream. Okay, so what's going to happen today? Let me mention the one other thing then that's important. Rainbow topics. So there is a GitHub repository. That GitHub repository is github.com/codingrainbow/rainbow-topics. And this repository is where I'm keeping track of this rather massive list right now of 103 things that I eventually hope to get to in my video series over the next however many years, decades, centuries that I do this, when they take my brain parts and attach it to a robot thing that makes robot video tutorials. I'm just practicing with the soundboard. By the way, if you have some sound effects that are that I can use, license whatever properly on this Coding Rainbow show, if you want to remix my voice saying weird, stupid things, or your own voice saying weird, stupid things, please send those to me. I can fill out this soundboard. Right now I don't have too many things, but I do have, never forget, this dot song. Okay. Now, everybody always thinks every time somebody says I seem to have gotten a haircut, and it's just not true. I have not gotten a haircut. Okay, so you, first of all, a lot of these are things that I posted and keeping track of myself. And some of these things are requests from viewers. Some of them are questions that I answer in my Q&A series. But I encourage you to come here and search through to see if the topic you're interested in is already there. If it's already there, what you should do is, this one actually, so I'm going to do this right now. This one under neural networks, number 111, M.L. Wyatt writes, I think this could be considered a duplicate of number 63. Oh, whoa! I think this one, and then there's one, this isn't even what I was thinking. There's another one called machine learning, which I plan to cover neural networks in. So there's a lot of duplicates. So I'll close these. I'll do this later. I'll clean this up later. The point is, what you can do is also thumbs up a topic that you like, because I'm going to go back to the issues list, and I'm going to do sort, and I'm going to do sort by this thumbs up button. And we will now see what is rising to the top here. These are the things that are kind of most requested currently right now. Machine learning, which I have some maybe announcements I could make about my plans for the machine learning set of tutorials that I hope to do. Computer vision, of which I have done 5 or 6 videos so far, and I have plenty more that I intend to do. Delaunay triangulation, how interesting. That one has somehow rise to the top. So I will look at that at some point. Chrome extensions I have slated for the fall. I plan on making videos for a course that I'm teaching at NYU this fall through this live means. So that's one of the week's topics in the fall, so probably September or October. Look for that. And then genetic algorithms. So I'm going to do, this is what I'm going to do today. Genetic algorithms. Oh, it's not a button. At some point, I'm overdoing it with the sound effects. I might have just, the first time I press the button might be me overdoing it. But you guys will let me know if I've reached that threshold. Okay, so now, what about this genetic algorithms thing? So let me first mention to you, as a little bit of background, I have a book called The Nature of Code. You can go to thenatureofcode.com is a website. I am going to go here now to read the entire book online for free. I have it all in HTML. I'm going to go click here on, chapter 9, the evolution of code. So there is, I do have this full tutorial, which covers a lot of the general concepts and examples that I intend to show you in this session today. So first of all, that's a supplemental resource for you. The other thing that I will mention is currently on YouTube. If I go, let's see, if I Google Schiffman, YouTube, genetic algorithms, you will see there is this particular video that exists. So I'm not going to click on it and have it play right now, but this video is actually about 45 minutes to an hour long, and it's a recording of a presentation I gave actually at Kickstarter headquarters 3 or 4 years ago, perhaps, on genetic algorithms. So it does exist. A sort of tutorial about genetic algorithms in video form, but it's one of those like I'm talking to an audience and the camera's kind of over there, and so it's different style than this Coding Rainbow thing. Now, okay, so those are resources that exist already. The other thing I'll mention is that if you go to cadenze.com, which is a company that provides online courses on various creative coding topics, This course that I collaborated with them to create, which is available right now that you can watch all the videos, has an entire session on genetic algorithms. 5 or 6 videos about genetic algorithms, and those are edited and produced and very high quality. So in my mind, this summer, as I've started kind of spending more time doing this coding rainbow stuff, I thought to myself, I'm not going to do, I have 100 GitHub issues with topics that I could do about programming on GitHub. So I'm just not going to do genetic algorithms because I have the book chapter, I have this video presentation that's on YouTube, there's the Cadenza course, but I have been hearing from you, the viewing audience, however many people you might be, somewhere in a small number of people around the world, that that you would still enjoy having a set of tutorials made in the vein, in the style of this kind of free-form live stream, answer questions, make lots of mistakes, coding rainbow thing that I'm doing. So that's what I decided to do today. It is now about 11 minutes into this live stream. It is 10:50. I want to get started in the next 5 or 10 minutes because it's a lot of ground to cover, and I only have until about 1:30, which is still a lot of time to be doing a live stream, but we'll see how far that we get through all this stuff. So, so somebody in the chat asks, what is written on your t-shirt? And it says, people do, unfortunately you can't really see it because I have this mic clipped here. So it kind of like hides the text, but it says people doing strange things with software. This is a processing t-shirt. I hope that processing, we will be able to make more t-shirts available again soon. I forget where this quote comes from. Let's Google it, doing strange things with, somebody in the chat will tell me. I forget. I feel like this quote comes from a conference or something, or who knows. Okay, so I'm not going to worry about that right now. Somebody will tell me. Okay, let me mention one last thing that I want to really thank people about. I'm actually going to log into my YouTube channel here. I'm going to go to my kind of admin panel. I'm going to click over here under community, and I'm going to go to manage subtitles and closed captions. So right now you'll see, right now I don't have any contributions pending at this moment. That's because I have approved them all, but I want to show you here, I'm going to click under published. These are all caption submissions that viewers have submitted in English, in Spanish, in Dutch, in Russian, in French, in Swahili, in Portuguese, in English, in German, in French, in English. It is my goal to have every single video that I produce captioned in English and as many foreign languages as possible to make things as inclusive and accessible as possible. So if you are interested in contributing with this and have an afternoon to just caption one video one day, I encourage you, especially if you can caption them in English, because it makes those who want to do the foreign language captions, it often makes it easier to be translating existing English captions than to have to like listen and translate at the same time. So if a lot of you ask, like, I love what you're doing, how can I contribute? This is one way that you can contribute. Now, I should say, while it might seem that I'm just doing all this stuff out of a generous spirit for the good of the world, I am doing this in a sense also as a income generating thing. It's really not generating any income at the moment, but you'll notice I do have YouTube ads on. I do have this crowdfunding website. This also feeds into, I make these videos, and then my students at my job at NYU where I get paid can also use these videos. So don't worry about giving back too much. Just watch, just enjoy, send me your feedback. And I appreciate you just being a viewer and engaging in the community of people who want to make coding seem more inclusive and friendly and a supportive environment for anyone and everyone from all walks of life who wants to participate and learn and be creative. Okay, that's my platform speech or whatever. I don't want to get into some of that stuff. Okay. People in the chat are making lots of requests for coding for topics for future videos. I am not keeping track of those right now. If you want to suggest those topics, go to the Coding Rainbow Topics GitHub and file an issue. Okay, so what I'm going to do now is I'm going to put on a little music because I am going to start. I should do this stuff in advance, but I often just don't have time. I'm going to start downloading my examples. Oh, let me say something. So something that's going to be a little bit different about my genetic algorithm session today, I have most of the time what I do is I live code examples from scratch. But what I really want to do is talk through the concepts, how they work, and show you code examples and explain code examples. And a lot of these code examples are particularly long and complex. And if I were to code them from scratch, while I think that would be interesting, it would kind of take the full amount of time. So I think what I want to do is treat this more as instructional lessons, less of sort of code, challenge code from scratch. But what I'll do, probably not today, I mean, if I have time today, I would love to, but maybe we'll pick a topic or two, like somebody had mentioned the traveling salesperson topic. Yes, Oliver says, I'm late today, it appears. Usually I'm really late, but I was quite on time today, so you probably weren't really late. You were sort of on time with my pattern. But maybe afterwards I could do like a coding challenge where I do a genetic algorithm from scratch also as like another video. Okay, so let me put my music back on.
Cutting rainbow.
Wait, no, where's...
Dan Schiffman.
No, that's not it. No, that's not it. No, that's not it.
Cutting rainbow. Cutting rainbow.
Cutting power.
Yes.
Cutting power. Cutting power.
Theme song is coming. I might have it next week. Oh wait, I forgot. I was putting on the music as background music while I get the examples together. So first let me go here. Let me pull up this genetic algorithms. So this is kind of my loose outline. I want to go over the algorithm in general. I want to look at the Shakespeare Monkey as a kind of problem to demonstrate all the pieces of a genetic algorithm. I want to look at something that ties back into other examples that I have to do with motion and simulation, and then look at these other two techniques in genetic algorithms called interactive selection and ecosystem evolution. I actually meant for that to say like ecosystem simulation, but whatever. Okay, so where am I going to get these? You know what I'm going to do? I'm going to go to GitHub. No, I'm going to go to examples. So first thing I want to do is I'm just going to download I'm going to use both processing and P5.js today, mostly P5.js, but I will also use processing. So now I have these examples. I'm going to put those on the desktop. Then I'm going to go to the P5.js versions of the examples. And I'm going to download those. Didn't take very long to download. And then I need to open up terminal. And I'm going to change to the desktop, P5.js, and run a local server so we can see, do my examples exist? I talked about that, I talked about this, talked about this, I talked about this. Oh, something else I've got to get. Okay, hold on. Mozart or some smooth jazz. Yes, I'm interested in all possible music selections that you guys would, and honestly, I would pick all sorts of interesting music, but you know, I don't think I could just use copyrighted music on this live broadcast without paying a fee for it. So, which I would, you know, in many ways be happy to do to some independent artist or something, but not that I'm that popular that would really make any difference. Okay. Okay, I was going to localhost. Genetic algorithms, here we go. So let's just see how this is going. Good. This is one of my examples. I'm going to give myself a little bit less space here. Do this. All right. It's okay. Okay, so that's one of my examples. It's running. I have this. This is my outline. I'm going to keep that. I'm going to open up the Addendum editor. Let me close these. Close this. So I'm just getting set. Oh, I lost my music. As always, I always forget the this dot, this dot, this dot, this dot. I'm going to do this dot, this dot. I'm going to do this dot, this dot, this dot. I'm going to do this dot, this dot. I'm going to do dot, this dot, this dot, this dot, this dot.
Okay, let me.
This dot, this dot. Never forget the this dot. This dot, this dot.
What am I looking for?
This dot song. This dot, this dot, this dot. Never forget this dot. This dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do dot, this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot, this dot song. This dot, this dot, this dot. Never forget this dot.
So let me get this over here.
This dot, never forget this
And
dot. I'm gonna do the this dot, this dot, this dot, this dot, the this dot song. Never forget the this dot. Somebody composed that song for me. This is an example. I'm just gonna let it run for a little bit. Talk about it at the beginning of one of my videos. This one works pretty well in processing, just because it kind of draws a lot of stuff. Okay, so I have that example. Oops, did I just close that? Oh, I'm an idiot. Okay, and what I meant to close is this. So I have my text editor, which, you know, is probably going to start with this example. I have my browser open. I have processing. If I want to look at some processing code in relation to this, I have this here. Okay, so I'm just getting myself set up. I've got processing. I've got a browser open. I've got Addendum. Okay, one more thing I need to get. Where do I have this? Okay, now, oh shoot, I'm gonna go here into my, I have like a little slideshow of diagrams that I might want to use. Let's see if I can find this. Sorry, I'm gonna, here we go. I think this will do. Let's bring this over here. Is this a PDF? Oh no, that's a keynote presentation. I don't want that. Ugh. Can I go to where I just was? All right, hold on. Let's play along with me for a second here. Okay, I need this. Delete. Delete. Upgrade. Fine. Sorry, everybody. I'm getting myself organized. Delete. This works. This works. These are good. I'm going to use these slides. Ooh, this is interesting. Yeah, I can use this. Sure. Now let me export to PDF. I think that'll work best. Image quality, best. I don't have my bell yet. I was going to order a bell. I forgot. I need some.
Coding power.
Okay.
Coding rainbow.
No.
Coding power.
Yes, that's the. There we go. So ga.pdf. Let's put this on the desktop. Where's my desktop? Desktop. Where's my desktop? Desktop. Okay, just about getting ready to get started. Just getting all my stuff together. So I can quit this, I think. And hold on, where? Desktop. One last thing here that I'm looking for. Come on, desktop. Yeah, there it is. Go over here. There. Go over here. Delete that. Clean up. Anal retentive coder. Anybody ever watch the Anal Retentive Chef with Phil Hartman on Saturday Night Live? I kind of want to do a sketch with just the anal retentive coder who just spends all of their time organizing indentation and white space and like getting all the windows placed around it. I'm gonna do that. I'm gonna do that soon. Okay. Okay, back, everything back. Give me everything back. I don't want this. It's not relevant. I do want this. I do want this. I do want this. And I do want this. Okay. Now I'm going to open up this, which is another thing. Let's go. So I have some diagrams and stuff. Boy, don't I look like organized? And I have some diagrams and stuff that I will use throughout these sessions. Okay, great. This is so like, this is very not me. Hello and welcome to Evolutionary Computing. Item number 1 is traditional genetic algorithms. I will now explain to you item number 1. Okay. Okay. This. Can I make this like this too? And then when I go to full screen, we'll do this. And when I go out of it, yeah. Okay. Very exciting. Okay, I think I'm ready. So let me go back to my outline. The whiteboard is slightly visible. Thank you, Gabriel Film Studios. I actually can't see that because of the way that I set up this new soundboard thing. So I guess, I don't really care so much, but I guess I will fix that. Oh yeah. Oh my God. It's so ever so slightly visible. Also, what's down here is just, what's this? Oh no, this is a straw, by the way. What? See, I'll prove it to you. Yes. I'm sure everyone woke up this morning thinking, oh, I'm going to learn something about programming. But you know what I'd really rather do? Watch somebody drink out of a straw. On the internet. Okay. There. I think I got rid of it. I'm going to move the straw out of the way. There we go. I'm going to slowly walk back in. I think the whiteboard is still slightly visible. The whiteboard is visible. Okay. Yes, I do have, yeah. Okay, so here we go. So the first thing I want to do in this particular, hold on a second. Just want to check here. Yeah. The first thing I want to do is talk about what is a genetic algorithm, why do they exist, and where do they come from. So let me review in my head here for a second. Review in my head, I don't know what that means. I probably wrote something here about the history of them. Maybe I didn't. Come on. Oh, yeah. Okay, I guess. So I think this, maybe I'll mention this just at the beginning, that this work, Computer Simulations of Evolutionary Processes, dates back to the 50s. John Holland, adaptations in natural and artificial systems, and okay. Yeah, yes, Benjamin, I agree. So I really need something better. What I want, the problem with the higher stand for the laptop, which maybe isn't that much of a problem, is it would be here. Actually, I should just do this. Hold on. Let's give this a try. I know I'm getting sidetracked. But let's see how this goes. Can you see? This is an invisible, magical, invisible, no. Okay, so I'm going to try putting my laptop. Oh, a green cover for the back of my laptop. That's kind of brilliant.
So how much does it bother you that you can see my laptop right now in the frame? Does it bother any of you? And if I go to code stuff, mostly I have everything kind of over here on the right anyway. And then if I go do this, big deal. It's really just at the bottom. I think maybe it's okay. Not at all. In fact, you can enjoy my stickers. Over here, we have two SFPC stickers. We have a hello, my name is Dan. Oh, you can't really see that. I have to make it higher. Which is illustrated by Taeyun Choi. I have Peppa Pig. I think I have Sophia and I have Ariel. Snow White over here. I've got a lot of Disney stickers because I love Disney. Actually, no, my son and my daughter both put these stickers on my laptop. And oh, did I get distracted again? Okay, I'm gonna go back. No, there was a point to this. I actually came back here for a reason. Oh, no, which is to also say that I am wearing, in honor of Coding Rainbow today. Everybody, calm down. I might hurt myself by accident showing to you my socks. And then I swear I'm going to get started with the genetic algorithms. But if you can see here, oh, the green. This is green. Look, my hand passes through, but you can see that I'm wearing rainbow socks today. So my children picked out rainbow socks for me at the store. I said I wanted more rainbow clothing. I'm looking actually to get a rainbow. Genetic algorithms. Okay, you guys came for that. That's what I'm going to do. All right. How'd I do? 30 minutes. That's about my average before I really get started doing anything. So see, Oliver, you are not late. Okay. So I think what I'm going to do is start my tutorial with this particular chapter open. And then I'm going to move to this example, which I can talk about briefly. Then I'm going to go to this, oh, this doesn't, oh, no, whoops, that's weird. I'm again practicing it kind of works. Then, yeah, I have thought about wearing all green for a session. Maybe I'll do that sometime. Anuna in the chat writes, this is really unique. In a regular classroom, the teacher needs to wait for the students to calm down. Here, it is the opposite. Yeah, I'll say so. Then I'm going to talk about overview and mention John Holland and talk about search and the Shakespeare Monkey problem. I'm a little bit confused how to divide this up into separate videos. Obviously, I could just, this is one long video, but at some point I'm going to edit these into separate ones, and we'll see. Okay. All right, time to just get started. Okay. Here we go. Let me cycle the cameras. By the way, this is whenever I do this, this is what causes the camera to move slightly and the whiteboard to appear. But c'est la vie. I'm tempted to have music at the beginning of this one to do my weird. Hello, welcome to another, but I'm not going to. Hello and welcome to the first video in a new playlist. This playlist I don't know, what tense am I in? It is. You're watching it exists already. It's all about evolution, the field of study that is called. There was too much there. Okay, so let me try that one more time. It's got to get a little. I don't know. Okay. Hello and welcome to the first video in a new playlist. This playlist is all about a field of study that loosely you could call, one could call, I am calling evolutionary computing. And I want to talk about something that's called a genetic algorithm. I want to talk about why genetic algorithms exist, what they are traditionally used for, how you might apply them in different creative contexts, and go through a whole set of examples. So by the end of this, there'll probably be 4 or 5 videos showing you a range of examples and ideas of things you can try, as well as code that you can do in both Java using the processing framework and JavaScript using the P5.js framework. So that's my goal. That's what's happening. If you are interested in that, keep watching. If not, go and to a dance party. Okay, never mind. Sorry, I have a new soundboard. It's too exciting. Okay, so all of the stuff that you'll be watching, if you continue to watch, is based on material that is in a book called The Nature of Code. That I guess this is a book. I wrote this book, so that's why I'm using it, if that makes sense. And chapter 9 is the relevant chapter. So if you prefer to read in text rather than listen to me yammer on, you can go to this URL and check out this chapter. I'm going to kind of talk you through. Now, the field of evolutionary computing really dates back, I would say, to the 1950s. John Holland, working on different models of simulations of evolution in software. And so there's this problem that comes up in computer science problems and problems in life in general a lot, which is I need to find the answer. A single, tiny, little, optimized, perfect example in a sea of so many possibilities. It just would be completely impossible to check every single possibility until I find the answer. Now, that might seem a little abstract. What I want to do is talk about, and since I'm here, what I want to do is talk about this traditional genetic algorithms that was designed to solve those kinds of problems. So this is like a slideshow that's automatically playing. But over the course of this video series, I'm going to look at sort of 3 different scenarios. First, this traditional genetic algorithm that I'm calling it traditional, but it's kind of the original, the classic genetic algorithm, and then some creative twists on this algorithm, looking at this technique called interactive selection, which allows users and audience to kind of help participate in this evolutionary process, an ecosystem simulation to think of using genetics as applied to agents that are moving around the screen and experiencing this sort of artificial world. The video game Spore is quite famous for kind of having stuff like this built into it. So, but this traditional genetic algorithm, a good way to think about why this problem is necessary and how, and why this algorithm is necessary and how this algorithm can be applied is the Shakespearean monkey problem. So the Shakespearean monkey problem is this thought experiment that says, if you had a monkey typing at a typewriter for an infinite amount of time, typing randomly, eventually this monkey would randomly, by typing kind of every random possibility, type out the complete works of William Shakespeare. So while I think we could kind of probably agree that this abstractly as a concept is true, let's think about what this really means. So let's say there's a monkey, this monkey here, and this monkey, let's actually just say there's not actually a monkey. I don't have a monkey to bring in or anything like that. That would be interesting, though. We could try that in another video. But let's say there's a computer simulation of a monkey, okay? And I'm going to say that, let's simplify the problem and say that the only thing we care about is the phrase, to be or not to be, that is the question. Now that phrase has 39 characters in it. And let's say we have a simplified keyboard. I have a keyboard right here, which has a lot of keys and numbers and punctuation marks. Let's just say we have a simplified keyboard. And this keyboard has only 26 letters, lowercase, A through Z, and it has the space bar. That's 27 letters in total. So if you know about probability, I don't have a coin, but right, if you have a coin has a heads or a tails, you have a 1 out of 2 chance. There's one possibility being the heads, there's 2 possibilities in total. Typing at a keyboard, we can sort of say the same thing. If there's 27 keys, I have a 1 out of 27 chance of typing the T. Now, event probability, if you want to string two events together, if I have a 1 out of 2 chance of flipping heads and then a 1 out of 2 chance of flipping heads, I have a chance of flipping heads twice in a row, 1 divided by 2 times 1 divided by 2. So 1 out of 4 times, right? And you could think about that because I could type, I could flip, and here are my possibilities. Heads, 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 tails, tails, heads, tails, tails. There are 4 ways that I could flip a coin twice. Only one of those is heads, head. 1 out of 4 or 1 out of 2 times 1 out of 2. So the same problem here. The chance that I have for typing a T and then an O is 1 out of 27 times 1 out of 27. Okay, so even that is kind of like a very low probability. If I'm just typing at a keyboard randomly, it's quite rare that I'm going to type a T and an O. But it would happen probably in a day of me doing this over and over and over again. Now, the phrase to be or not to be, that is the question, has 39 characters in it. So in order for me to have the probability of typing a T, then an O, then a space, then a B, then an E, then a place, then an O, then an R, then a space, then an N, then an O, then a T. That's another song for somebody to compose. A T, then an O, then a B. Oh, no, space. A T, then an O, then a space, then a B. This is now, the probability is 1 divided by 27 to the 39th power. That's 1 divided by 27 times 1 divided by 27 times 1 divided by 39 times. Now, I previously, not right now or this morning, like a while ago, so hopefully this math is right, I did this math. And the actual answer is a 1 in 66, blah, 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 blah. It's a really massively like big, unfathomable number. So basically this thought experiment is, we were talking about genetic algorithms, right? So why is this relevant? This is like an artificial, this is a completely trivial problem, right? Because I'm gonna open up my processing code, I'm gonna make a new sketch, and I'm gonna say print line to be or not to be. Wait, I have to say that is the question. That is the question. So look at that. I have now just solved this problem of typing to be or not to be with 1 line of code. Dun, 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 dun. I don't have a sound effect for dun, 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 dun yet, so I have to make it, right? To be or not to be, that is the question. 1 line of code. But this can serve as an example problem, right? We know the answer. I know the answer is to be or not to be. There are 66 gazillion, zillion, zillion, gazillion possible random phrases, only one of which is the answer. I happen to know the answer, so I could just spit out the answer. But what if there's a problem that the search space is so vast that you couldn't possibly, and you don't know the answer, and you can't check every possibility? This is what a genetic algorithm is for. And I'm going to demonstrate this to you in a couple different ways in a moment. So let's go back, though, to this particular slide and just look at a little bit more about these numbers. So one thing that I did, let's say you have a computer simulation that is typing one, just to think about like really how the sheer vastness of this solution space. Let's say you have a computer simulation that can type 1 million random phrases per second. I don't even know if I can do that, if processing would run that fast. Probably could, but whatever. The point is, if I ran that, it would take, for me to have a 99% probability of at least that phrase coming up once, I would have to run that simulation for this many years. 9.719 gazillion, bazillion, gazillion, blah, 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 blah years. Notice, by the way, that the age of the known universe is this number down here. This number is a lot bigger than that. So these numbers are so incredibly sort of mind-blowingly huge that again, the reason that I'm here right now is to talk about genetic algorithms, and this problem is a good way for us to look at, okay, what is an algorithm that could even solve this problem without it taking this much time? And a genetic algorithm is that problem. Now, let's think about this more practically. One example that I love that's on the internet somewhere that I'm going to just pull up for you right now is called Boxcar 2D. I'm going to Google Boxcar 2D, and I'm going to run this right now, and I'm going to let this run for a while. So I think this is a nice demo. Oh, come on. Really? You're going to be so slow? Oh, you know what? I wonder if this page or this page, I'm going to close a few things just for a second. Refresh this page. Oh, I lost it. Refresh this page. Okay, so this is Boxcar 2D. I did not make this. I don't know why it's running so slow, but now it seems to be doing a little bit better. You could think about, here's the problem. I want to design a car. And I could say that, oh, I know. Oh my God. Time out. Maybe I'll edit this out. So something really funny just happened. I'm going to the other window here. I didn't realize that I have this like horrible key mapping problem. This is for the live stream. So I have a soundboard here.
Coding power.
Coding power.
Coding power.
Where the keys on this keyboard over here, number 1 and 2,
Coding power.
are mapped to these sound effects. I also have a Wirecast piece of software, which has 2 views. It has this view that you're looking at, and this view here of a whiteboard, which I was about to walk over to. And those are mapped. Those are mapped to these key presses. The problem is I can't have them both in focus at the same time. So if I want to use these key presses, and I have the soundboard, so I think I need another computer or like a tablet or something.
Coding power.
So if you can't see this, but if this computer has the soundboard software in focus,
Coding power. Coding power.
or if it has the Wirecast software in focus. So I think right now, just for the purpose of making this actual tutorial about genetic algorithms, I'm going to turn off the soundboard. We'll bring that back later. So yes, in the chat, by the way, I'm looking at the chat now. I do finally have a soundboard, but I don't have very many sound effects. Arno, who created a whole set of sound effects that I used in my sound tutorials, I have a lot of those programmed in here. And I have, oops, it's not running right now. But I can just use the mouse here over here. This dot, this dot, this dot, this dot's on. And I need to get F looper. I think F looper I saw in the chat. I need to get F looper sounds in here. I somehow don't have those. I don't have this sound effect. Okay, so, but I got to go back. I need to think of another. I didn't anticipate this problem. So anyway, I'm going to go back into my tutorial. Hopefully I'm making sense and being interesting so far. You guys can let me know. And I was going, what was I going to? Ah, yes, okay. So let me just see, is this working now? And actually now I can just do this. So I don't need that button anymore, I just have a keyboard. Okay, here we go. So this will get spliced together without the crazy thing that happened with the sound effects. I guess what I can do is do this, and then I have my sound effect, and then I can, whoops, do this, and I have my switch. So I can, if I get good at this, I can do this. Okay. Yeah, I don't want to get too lost in this right now. Gabriel asks, can't you change the keys to press? And I could use different key mappings. The problem is I have 2 pieces of software, and one has to be in focus to receive the key mappings. But I do have an idea of a way around that, but I'll have to think about that. Okay. Oh, and I don't actually even have the light turned on the whiteboard because it's so hot. So that's another light. So it's good that I didn't do that anyway. Here we go. Whiteboard is a little cut off at the top, but that's okay. So here we go. I'm going to continue this tutorial. So let's say I'm a car designer and I know, okay, I'm going to design a car. I want it to be aerodynamic, so it should look like this. I want it to have, small wheels in the front and big wheels in the back. And because I like rainbows, I want it to have a sign, with a rainbow on it. And I also like unicorns, so I wanted to have like a unicorn thing at the front, but I have no artistic talent, but this is the best I could do, and I've designed this car. This is like me designing a car. But here, let's think about the possible ways. Let's say I could design a car out of, here are my things, any polygon. I could design a car out of any number of wheels. Those wheels could be attached to the polygon any number of ways. And I could have any mythological creature. I don't think this part is in Box 2D. Mythological creature. Somebody make a boxcar 2D with mythological creatures like unicorns. That'll be exciting. So you can see, like, if we started working this out, I probably would also have gazillions and gazillions and gazillions of possible car designs. So one way of finding an optimized car design is to evolve that optimized car design. And if I come back over here and press my button, you can see that's what Boxcar 2D is doing. It's testing out a whole lot of different possible car designs. It's using the Box 2D physics engine. I do have some video tutorials about that. So this is ultimately what I'm building to. How can you design a system that uses evolutionary algorithm to evolve a behavior or a design or solve some particular kind of search problem. And there are lots of ways you can apply genetic algorithms. And what I'm going to do in this tutorial series is start with a simple problem with a known answer. And if we can get the genetic algorithm to solve this simple problem with a known answer, then we can take that genetic algorithm and start to apply it to lots of other interesting scenarios without known answers. And the simple problem with a known answer that I want to solve is this one. To be or not to be, that is the question, without a brute force search. So I could make a brute force search that just tries every possible or I could create an evolutionary search, a genetic algorithm search, and that's what I'm going to do. And in that, and that will cover the sort of traditional genetic algorithm. What are the pieces of the algorithm? How does it work? And how do you implement that in code? So this video is my brief sort of overview of kind of covering where the stuff is coming from, what I'm thinking about. And in the next video, what I'm going to do is actually start talking you through the algorithm itself and starting to write pieces of code that implement that algorithm and show it to you in the context of the Shakespeare to be or not to be, that is the question example. Okay, thanks for watching, and maybe I'll see you in the next video. I don't actually see anybody, and if you're watching this in a video, I'm just recorded, so I'm not actually even a thing, but I am a real person, and you could say hi to me sometime if you wanted to, somewhere. I don't know where. Okay, bye. Okay. How was that, everybody? Improvised introduction to genetic algorithms. Hopefully that was good. I'm practicing.
Goody power.
As always, I always forget the this dot, this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do dot, this dot, this dot, this dot, this dot, son. This dot, this dot, this dot. Never forget this dot. Okay. So, Dan, are you going to do the cat? Hold on. Pause music. Are you going to do the cat evolutionary example? Yeah, I think that's this same example. Usually what I do, this is the same as what I did in the cadenza course, is usually what I do is I start to describe the algorithm with a sort of simpler phrase, like the phrase cat. Would you like to suggest another phrase, like puppy? I don't know, kitten? Yes, Nuno makes a great suggestion in the chat. You only need to make a software to generate videos, change a bit on every iteration, and after a few generations you have very good videos. Okay, it's very hot in here. One of these days it'll be winter again, or I'll set up my studio in a place where there's air conditioning. Life will be a little easier. I can wear my rainbow sweater. I need to get a rainbow sweater. I need one by next week because I have this plan. Okay, oh, unicorns. I don't know why I didn't think of that. Good idea. Okay. Unicorn is still a little bit long. Winter is coming. Yes, indeed. I want to talk about Game of Thrones now, but I won't. Big fan, big fan. Okay. Okay, so let's see here. What I want to do next is I'm going to close up. I'm going to leave this running, actually. I think I'm zoomed in a little bit. I want to go to localhost. I'm trying to remember what I wanted to show is this. Yes. So I'm going to go to the code for a second. Just want to show something. Okay, so this is, by the way, brute force solution. So this is what I will start with here. And then what I want to do, Pokemon. Yeah, by the way, I almost canceled this whole genetic algorithms thing because I saw somebody doing like Pokemon mapping stuff with like a Python script that hacks like the server protocol. And I was like, oh, I should just do like a video about that on Friday. Because then my YouTube views, Pokemon, what could be more, I don't know. But then I decided not to. Okay. Okay. I'm sweating. Can you guys see that I'm sweating, by the way? So let me turn the fan, move the fan a little bit. Okay. So what I want to do in this video is look at, yeah, I believe I am broadcasting to Facebook, by the way. This is showing up on Facebook. I'm not checking the chat. By the way, if you're watching this on Facebook or Twitch, I think I'm broadcasting to both of those outputs as well, but I only check this chat. I only look at the chat on YouTube. Okay, so I'm trying to think of what the next step is. I think the next step, I'm about an hour in, is to talk through the algorithm itself. In other words, okay, so I want to talk about sort of three key principles. Usually, by the way, I sketch this out on the whiteboard. I have these like slides, which is so unlike me to use, but I might use them anyway. So I want to show, okay, I think what I want to do is show this as a representation of the brute force random phrases. This being the actual genetic algorithm running to solve for to be or not to be, and you can see that it's eventually going to get there. It got there. And then what I want to do is go through the algorithm itself. Then I want to talk about these principles, talk through the algorithm itself, and then maybe that's it. And then the next, so there'll be two videos. One just to talk through the entire algorithm, and then the video after that will be to look at all the pieces of the algorithm in the code. Okay. The random noise. Oh, thank you for pointing that out. Okay. Well, the good news is, in theory, the random noise is only causing a problem in the live stream, but I'm recording everything to disk. So the quality of the video that's recorded to disk should not have that problem. Dale asked, do the videos end up at GitHub? Yeah, I haven't done a good job of this, but the videos, they end up at YouTube. That's where you can watch them. But I always then try to post to a link to them from that GitHub issue thread. So if you're following the GitHub issue, etc. Okay, I got to get moving. So I think I'm going to live with the video quality issue because I think it's worth demonstrating this. I will try to not stick on it for too long. So here we go. Okay. When I upload it to YouTube, we'll have that problem. Well, it's only going to be brief. Uh-oh, I'm running out of my coffee drink. Okay. Here we go. Let me cycle the cameras. Part 2. Let's see. I think I probably should erase this. And come back over here. Oh, I'm getting much better at this now with my new system. Okay. Upload it in fake 4K. I think it's only going to be for like a few seconds that I'm going to show that, so I don't think it'll be too much of a problem. Okay. What did I say I was going to do in this video? Go through the actual algorithm itself and talk about 3 principles that are needed in... Okay. All right. Hello again. Okay, welcome to this second video in my new series about genetic algorithms and evolutionary computing in general. So in this particular video, I am going to talk through the actual algorithm itself. Now, if you can't remember what I'm using as my demonstration to demonstrate this idea of a genetic algorithm, I'm looking at the problem of finding the phrase to be or not to be, that is the question, in a sea of random to be or not to random phrases. So to demonstrate this idea, I have this particular P5 sketch running in the browser, and it's just generating random phrases over and over again randomly. Now, at some point after some gajillion amount of years, we might, it could happen right now. This could be the moment where we could be so unbelievably lucky and we would just all go buy our Powerball tickets, where to be or not to be actually appears right here, but I'm pretty sure that it's not going to. So this is the brute force problem. The solution to this brute force problem, I'm going to refresh this here, is to use a genetic algorithm. And you can see that this is now the example that I'm going to get to of the genetic algorithm running, and you can see it took a matter of 5 to 10 seconds to find this phrase, to be or not to be, and that is the question. It took a number of generations. There's this concept of fitness. There's this idea of a population. There's this thing called a mutation rate. So this is what I need to cover. What are all the pieces of the genetic algorithm? How do they work? What is the order in which they happen? And then after I do that, we'll start looking at how all those things are implemented in actual code. And I'll look at both JavaScript code that you can run in the browser, as well as Java code that you can run in the processing programming environment. Okay. So coming back to the algorithm, let's check out our car, by the way. So this, by the way, I'm just letting this run in the background. You can see that these cars from Boxcar 2D are really evolving quite nicely. I want to credit whoever made Boxcar 2D because I really love this project. So I don't know it off the top of my head, so I'll mention it in a future video and I'll make sure that it's in the description of this video. But you're going to have to go to the website itself and find it. Okay, so we'll check back in on our cars in a little bit, our cars. But right now I want to go back to this kind of presentation. So now, I don't usually use slide presentations in my videos, so feel free to complain in the comments if you want to. But before I even get to the algorithm itself, I want to talk about, now, I want to mention something. As with most of my videos that are part of the Nature of Code series, I'm doing a thing where I'm kind of saying, this nature stuff, this physics stuff, this biology stuff, it's really interesting. And I want to be inspired by it and try to kind of approximate it in software to create compelling and interesting and unique creative projects. But I'm not actually here saying to you, I'm a kind of like formal, rigorous scientist who's trying to do a formal experiment about evolution and model evolutionary processes precisely in software to study some type of actual biological process. The idea of a genetic algorithm is simply like this idea of inspired by actual events, right? Based on a true story. This genetic algorithm takes ideas from actual biological evolution and applies them in software. But I just wanted to sort of a disclaimer to say that I'm always kind of scratching the surface of the actual topics of genetics and evolution. But if you read Darwin and think about Darwinian natural selection, there are 3 key principles that need to be in place for evolution to happen. And those principles I want to make sure are in the genetic algorithm that I demonstrate to you. So first I want to just talk to you what those principles are. The first one is heredity. So if we're going to have this idea of elements of a population that evolve from generation to generation, there must be some mechanism in the algorithm in our code that allows data from one generation to be passed from one to the other. So that's one thing that's going to have to be there. Variation, right? Let's say I want to evolve whiteboard markers. And this is my population of whiteboard markers. I only have blue ones. And these whiteboard markers are going to somehow make children whiteboard markers. This is getting a little bit weird. But the point is there's no variation here. These are both blue. So they could make a child and pass down their traits, their data to the next generation, and they would be blue. And then there'd be more blue, and there'd be more blue. And I want to have some pink ones and some purple ones and some orange ones and all the colors of the rainbow. I'm off track here, but you get the point. There's got to be some variation. And what's the mechanism in order for there to be a variety of traits either in the population when it starts or as the population evolves over time? So that's another key principle, variation. The last principle, which must be present in the genetic algorithm, is selection. Selection. There has to be some way of saying, here's my, I can't believe that I'm using whiteboard markers. I should have thought about this in advance. And brought some like stuffed animals would have been great. Could have brought some stuff. That would have also been weird. Stuffed animals, weird. Yeah, okay. But anyway, this is my population of whiteboard markers, right? If I just say every single one of these whiteboard markers has an equal chance of passing its genetic information down to the next generation, next generations, next generation. Oh my God. then there really won't be evolution at play because nothing will, the makeup of the population, the quality of the population will not really change over time. However, if I were to say something like brighter colors are more likely to have their genetic information passed to the next generation, then I might be more likely to pick red or more likely to pick this green. I don't really have any bright colors, darker colors, whatever. The point is that there must be some process of selection. I should just read this to you. Mechanism by which members of the population have the opportunity to be parents and pass. So this is, by the way, typically referred to as survival of the fittest, right? This idea of fitness. And this idea of fitness will play a big role in the genetic algorithm. And fitness will actually become a mathematical function, which is somewhat absurd and not how things don't work in the real world. We're all walking around with a hat on, and then there's a number on our hat that says our fitness as a numeric quantity, and the higher our fitness is, the more likely we are to pass our genetic information, right? But this is this idea of this kind of almost cold, algorithmic version of this kind of beautiful and amazing natural process. I'm using sort of mathematical function to calculate fitness. Okay, so this is the idea. I must make sure these three principles are present in the genetic algorithm. So I'm going to whoop, that's our car. We're checking on our car again. It's not one car, by the way. It's been, actually, maybe it is. I wonder if it pauses actually when I take the window out of focus. But whatever it is, it's certainly evolving to do cool and amazing things. I want to go back to this. So I want to talk through how this algorithm works. And I'm going to use natural selection to pick this purple marker. And then I have to press a button, that button, to come over here. And let's talk about, now, what I want to do, I really want to use unicorn, but unicorn has too many letters in it also. Maybe I'm going to use unicorn. Gosh darn it, I always just use cat. Let's just say we want a simpler phrase to evolve. I could use rainbow, by the way, but I'm going to use unicorn. I want to evolve the phrase unicorn out of every single, it's not really a phrase, the word, the sequence of characters unicorn, out of every single possible random sequence of characters. So the very first thing that I must do in a genetic algorithm, in the sort of traditional computer science genetic algorithm, I don't know, I just said computer science. I have to put like a quarter in my computer science jar. I love computer science. This is just not a computer science YouTube channel. It's something else. I don't know what it is. Okay, step one is create a population. I'm going to write just pop for short. Can you read this? Create a population of n elements. And let's remember also down here, what are those three principles I must have? Heredity, I must have variation, and I must have selection. Now, I'm disappointed with myself. I wish I had written variation first in this order, because ultimately this is where we get, in this step, we get our first principle, variation. Now, the way I wrote this, create a population of n elements, I don't necessarily have variation there yet. I really should say create a, random, and I think this might be cut off at the top, but I just wrote the word random there. Create a random population of n elements. And really, I didn't write that very well. I should say create a population of n elements with random genetic material. Now, what is this genetic material? This idea of like sort of virtual DNA, digital DNA. We're gonna have to look at how that's encoded in code and stuff later. But you can think about it again. Let's think about it in the context of trying to evolve this phrase unicorn. The population might be a whole lot of 7-character words with random characters, like jorm, pancake. That's the right number of characters. This is really much harder than I thought it would be. I think that might have two. Anyway, so you get the point, right? This could be our population. Unijorm, pancake, and Boy, I'm doing. So this is a population that has variation. Now, does this have enough variation? With this idea that we're going to somehow mix and match these over generations, could I actually get, I have uni here, I have a C here, but I have nothing with an O in this spot, nothing with an R. Oh, maybe I do have an R, nothing with an N in that last spot. So the variation, there's more to variation than just that initial population, which I'll get to, but that's sort of a key principle. Okay, so that's step number one. Great. And actually, you can think of this in the sort of P5JS and processing world of we have a sort of initialization and then a forever loop. This step 1 is actually the setup function. This is what will happen in the setup function. Okay, step 2, which I'm going to draw a line here because this is what's going to happen in the draw function, meaning step 2 is going to happen over and over and over again. For generation, 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 evolving, evolving, evolving. Step 2a is calculate fitness for, n elements. So we want to calculate the fitness of every single member of the population. This, by the way, is playing a role now, this idea of selection. Fitness is going to be a means, a mathematical function to determine which members of the population are more likely to be selected to pass their genetic material down to the next generation. So that's this idea of calculating a fitness. So there's going to be some sort of loop that will go through all elements of the population, call a function that will calculate the fitness and give you some number back. So let's think about what could be, so one of the key factors in a genetic algorithm is the fitness function. So what could be, think about it, what could be a fitness function here for this particular problem? Well, I have these 3, my population has 3 elements. Instead of n, it's 3, right? And I could calculate the fitness for these. I could say the fitness function for each element of the population is the number of characters that match the target phrase. 1, 2, 3, 4, 5. So this has a fitness of 5. 1. This is a fitness of 1. Oh boy, this one did terrible. This has a fitness of 0. Okay, I might need some different example in a second. I got one for you. Popcorn. And this one has a fitness of 4. This is actually going to work out beautifully for me. So unijorm, pancake, and popcorn. Hopefully I did that right. So you can see that these all have a fitness score. Now, ultimately, there are many things that one needs to do to refine fitness and make a genetic algorithm perform more efficiently and faster or less fast or whatever, but this is kind of a simplistic version of a fitness function. Okay, great. Now, what we now need to do is this. So that's step A. The next step, I'm really just going to call kind of reproduction or selection. I think actually this sort of whole thing is that. So this step B has now 2 parts to it. 2a, b, lowercase a, b1, I don't know, whatever. I have a terrible numbering system here. But the first thing that we need to do, this also needs to happen n times. So what needs to happen n times? And that says reproduction section. That should say, I'm just going to use my hand here, selection. Pause, timeout. This is going to edit point here. I'm kind of dying here. It's totally fine in here if I have the fan pointed at me. And I have the way that I had the fan pointed was pointed at where I stand with the computer. And at the whiteboard, I just was starting to feel like I was going to pass out. So now I have the fan pointed over here, which is much better while I'm at this whiteboard for a while. So I'm going to have Mathieu, thank you for editing this little part out where I talk about the fan. Okay. So the overall goal of the genetic algorithm, wait a second, I just want, while I'm doing this, everything okay in the chat? Drink beer, okay. It is computer science. I don't know why I made that lame. Someone's going to get very angry at me on the internet probably for my, whatever. Okay, coming back to this. Sorry guys. This takes a surprising amount of energy and concentration to do this. the ultimate goal of this genetic algorithm is to end up with another population of n elements, right? This idea is we start with this random population, we calculate their fitness, this next step of reproduction at the end, we should have a new population of n elements and then go back to calculating their fitness again and doing this over and over and over again. Their fitness scores over time should be getting higher and higher and higher as a whole, as a population whole. So this reproduction selection step is a multi-step process. The first thing that I need to do is pick two, and for lack of a better word, I'm going to call them parents. And two is somewhat arbitrary. So there's a lot of parts of this genetic algorithm that you can kind of play around with. Certainly, you could say that the way that reproduction works in your genetic algorithm is a single element just makes an entire copy of itself. Another way of saying that is that two elements come together and mix that genetic information and make a new member of the population. You could say that three elements come together. This is all just sort of made up as an algorithm, and you might have kind of creative takes on this. But the sort of classic genetic algorithm kind of follows this idea of two parents. So how are those two parents picked? Well, this is an interesting thing. And by the way, we're really talking about selection here. We're now in the third principle here. The way that those two parents are picked, there's a bunch of different ways, by the way. First of all, you could just say, you know what, I'm just only going to ever pick the top two scoring parents. So I'm going to pick Unijorm and Popcorn. And I'm going to make all the children from Unijorm and Popcorn, and we're going to have a lot of Popjorms. I love Popjorm. It's my favorite snack. Popjorm. I'm going to mix those two up and make a lot of Unijorm Popcorn children. But really, Pancake, even though it only got a score of 1, we wanted a different way of doing this, a kind of better, the sort of more traditional way of doing this with a genetic algorithm, is not just to pick the top two, but to actually pick from the entire population, but assign the probability of an element being picked to its fitness score. So the reason why these numbers worked out so nicely is I could write them a different way. I could say 50%, 40%, 10%, 0%. So you could think of this as possibilities. What I'm going to do is I'm going to pick out of a hat. And out of that hat, I have a 50% chance of picking Unijorm. It's going to be picked 5 times as much as Pancake. Popcorn is going to be picked 4 times as much as Pancake. So I could use those fitness scores to assign them to probability. Another way of thinking about this, I've kind of run out of space on this whiteboard, but I'm going to use this spot right down here, is I could think of a kind of wheel of fortune spinning wheel. So Unijorm gets 50% of the pie. Popcorn gets 40% of the pie. This is Popcorn, this is Unijorm, and this is Pancake. So the strangest breakfast ever. And you could think of this sort of spinning wheel here. So I'm going to spin the wheel, and most of the time it's going to land on Unijorm. Often it'll also land on Popcorn, but every once in a while it'll land on Pancake. And that's how I'm going to pick those two parents. So the higher the fitness, the more likely that element is to be selected. So that's step one. Once I have those two parents, I'm going to make a new, and I'm using the word element just to be a sort of word for a member of the population, a creature, element, thing, but I'm going to make a new element. And making the new element is a 2-step process. One step is called crossover, and another step is called mutation. And this is, by the way, where we get our last key principle from Darwinian evolution. So we had variation because we create an initial population of random elements. We have selection in that we calculate the fitness of each element, and we use the fitness as a probability. It's sort of selection probability. It's probability of being selected as a parent. And now, to make that new element, we have to have some mechanism by which the genetic information of one element gets passed on to the next generation. So I'm going to come back up here. This is my weird paper towel whiteboard eraser. Slightly wet with water, because that seems to work well. And I'm going to describe to you the technique of crossover. So let's say we have Unijorm, and we have Popcorn, right? I don't know why I drew this line here, right? These are two members of the population. The mechanism of crossover says take half of the genetic information, and the genetic information is really just this sequence of characters. Take half of the genetic information from one, like uni, and then take half from the other. There's 7, so I'm splitting up 3 and 4. Take half of the other, like corn, combine those two, and look, we get unicorn. Now, of course, that's not going to happen magically instantly with the first 2 things you pick. This is artificially designed to give me the right answer, but this is the idea here, that to make the new members of the population, you take 2 that got a high fitness, you combine those, taking 2 with a high fitness to make a new one, you have a good chance of getting a child with an even higher fitness score for that next generation. So this is the idea. Now there's a lot of different ways that you can do crossover. You can actually just pick a random midpoint. So sometimes you just take 1 from the other and 6 from one, or 5 from one and 3 from the other. You could do something where you like alternate. Take U, then O, then I, then C, right? Or you could flip it. You could have a 50% probability for each one. You could turn this into binary information and mix up the zeros and the ones and then convert those back into characters. There's all sorts of ways that you can do crossover, but you'll see what I'm doing in my example, which is kind of a conventional way of doing it, is picking a midpoint, taking half from one and half from the other. And as you'll see, these characters are stored in an array. That's what I'm going to get to as soon as we look at the code. So that's crossover. Now, we could say that I'm done. This is it. This is a genetic algorithm. Make the random population. Calculate all the fitness. Create a new generation with crossover. Calculate the fitness again. Create a new generation with crossover. Calculate the fitness again. Create a new generation with crossover. Over and over and over again. That could be it. However, there's a problem. In the case of not having enough variation in the initial population, which is quite a reasonable thing to have, it is often useful to artificially introduce additional variation into this process. So 2 elements of the population are combined with crossover, but before that child is finished, a mutation is applied. And mutation is typically referred to as a sort of percentage rate. So I might say there's a 1% mutation rate. That means for each one of these characters that was selected, that was combined with crossover, there's a 1% chance that I'm actually going to mutate these characters. What does mutating mean? It could be that I just pick a new character. It means that I could go up or down in the alphabet. In this case, none of that would really matter. My mutation is just going to say there's a 1% chance that a random character is selected instead of the character that comes from crossover. And this keeps variation in the system. This mutation rate, as I'll show you in a little bit when I run the example again, really affects how the algorithm behaves. Is there a lot of randomness, less randomness, that sort of thing. So this really completes the genetic algorithm. This is we have heredity as part of crossover. That's the mechanism for heredity. We have variation in the way that we create the initial population and the way that we use mutation as that last step of making the next generation. And selection as this way of calculating using a mathematical function to assign a fitness score to each element of the population, as well as then using that fitness score as a probability for how that element of the population, whether or not it'll be picked as a parent to pass this genetic material down to the next generation. So in the next video, I'm going to say a few more things, and then I'm going to save looking at the code for the next video. So I'm moving a fan here and this over here. So I'm going to come back over here. My computer went to sleep. Come back. There it is. So I want to run this example. Actually, let's check on the car again. And let's think about this for a second. What are some of the steps of the population here? So you can see one thing that's a little bit different is it's kind of doing them all one at a time. So we're seeing one member of the population, but we can sort of think of certain pieces here, like what is the fitness function in this particular simulation? I would assume the fitness function, which you can see here is represented as score. None of these have really gotten a score yet. Come on, let's get, you can see it got a score. It's probably how far did it travel in a certain period of time. So that I would assume, and you can see as the score for these. So that's one thing. Then, you can see, like, as you look at any example of a genetic algorithm as it applies to evolution, you can find the pieces of the algorithm. So let me just look here and see how did we do here. This is a representation of the algorithm. You can freeze frame this if you want. It's also on the Nature of Code website. But you can see this is basically everything I described to you. Step 1 is initialize, create a random population of n elements, each with a random DNA. Step 2 is selection, evaluate the fitness of each element of the population. Then step 3 is reproduction, pick two parents, apply crossover, apply mutation, add the child to the new population, and then step 4 is replace the old population with the new population and return to step 2. So set up this, everything happens initialized, draw happens over and over again. And this is what I'm going to look at in the code in the next example. Great. So actually, I'm gonna end this video now. And in the next video, what I'm going to do is look at how the code works, play with some of the parameters, and see how the genetic algorithm behaves. Okay, thanks for watching. Okay. I see that there's a lot of chatter going on in the chat. I got 82 people watching. How is this, everybody? How's this going so far? I might need to get a drink of water. So let's see here. I'm looking at my watch. It is noon. I said till 1:30, so I'm about halfway through the amount of time that I allotted for myself, which is pretty good. I've got 2 kind of really introductory videos. I'm not going anywhere. Andrew Kim says awesomeness, good, I'm glad. Very interesting topic. Genetic algorithm, awesome, finally. Okay, I'm glad you guys are enjoying this. It's good to have. Sometimes if I'm teaching in a classroom, maybe I'm just like a person who needs a lot of like reinforcement, but you can kind of get a feel for the room very easily, and I can kind of have a sense if people are asking questions. And sometimes I lose my train of thought and whatever. It's sort of hard in this context, which is why it helps me to play music. Is splitting, okay, Minecraft Chris asks, is splitting the genetic information in half better than randomly choosing any letter? I would say it depends, and there's really no one answer to that question. In this particular example, I think it doesn't matter. I think you would probably get the same result either. I do think there are some aspects of how I'm calculating fitness, though, that I do want to cover that are important. Hill climbing algorithm is part of genetic computing, isn't it? Yes, that is correct. In a way, that's what we're doing. If you think of the solution space as a topological map, where the correct answer is at the highest part of a hill, we're sort of, as we're kind of like searching for it, we're trying to find, we're randomly picking places in the topological map. And if they have a good height, we're going to look around those places and see if they get better heights, and then look around those places, that sort of thing. How would you do the mutation? So that I will cover in the next part 3. So I'm about to start kind of launching into part 3. I think I'm going to get a glass of water. So what I'm going to do is, as always, I always forget to play you guys the this dot song, and I'll be right back. I'm muting my microphone. I'm going to do this dot, this dot, this dot. I'm going to do this dot, this dot. I'm going to do dot, this dot, this dot, this dot, this dot song, this dot, this dot, this dot. Never forget this dot, this dot, this dot, this dot, this dot song, this dot, this dot, this dot. Never forget this dot, this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do dot, this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot, this dot song, this dot, this dot, this dot. Never forget this dot. This dot, this dot, this dot. Never forget this dot. I'm gonna do the this dot, this dot, this dot, this dot, the this dot song. Never forget the this dot. Somebody compose that song for me. Okay, wow, that was good timing. That song is about exactly the amount of time it takes me to get a glass of water. Okay, so let's see here. What I want to do now is pull up the code. I forgot about this example that I was running. I won't worry about it. I'm gonna turn off the cars. Right, okay, so this is a good question. I should cover this in the video. So Gabriel asks, it wouldn't really go with the evolution thing, but wouldn't it be better to choose the letters that are right? Yes, so this is an important point to remind ourselves. this problem that I'm doing is totally meaningless because I know the answer. So I could just pick the right letters, or I could just type the answer, right? Don't need to solve this problem. So what I'm doing though is artificially using the genetic algorithm and limiting myself to that technique as a way of solving the problem to demonstrate the genetic algorithm. And if I get the right answer, then I know the genetic algorithm worked. But and then once we have that, we could apply it to actual more interesting problems where I couldn't just pick the right letters because maybe I don't know what the right letters are. But you're right to think that. Like, this is not a session on how to most efficiently select to be or not to be, because I could just do that in 2 seconds. Okay, so so I want to fix a few things. I feel like there was I want to fix this annoying average fitness thing. Before I go on, I want to how's this font size is very small, isn't it? Is that better? Is that big enough now, this font size? Okay, so what I just want to do is average fitness. Oh, number format. Does number format work in P5? If so, I didn't do it correctly. Yes, number format. Oh, you know what I could do? Even better. I'm just going to do this. Floor 100 times plus percentage. Let's try that. Yeah, I like that better. So I just wanted to have this average fitness value be something that's a little more legible. Okay. Total population, mutation rate. Okay. Font size is good. Yeah, so just one more question I'll answer in between this stuff here is B100DYH311 asks, is that the starting template for this problem, or did he work on this code before in this video? So what I'm doing, which I don't typically do, is I'm just using pre-made examples that I made for my Nature of Code book and showing you the pieces, highlighting the pieces of the code and demonstrating them for you rather than write them from scratch to kind of make these videos. Yeah. Okay. I cycled the camera, I believe, just now.
Goody power.
I think I might have heard something there. Okay. Okay, I think I'm ready. I'm getting good at my keyboard shortcuts, getting better at them, and I love having this up higher. I feel like even though I'm still looking down at the screen, I am a little bit more connected eye contact-wise. Okay. Let me make sure there's no emergency messages on my phone. Ooh, hold on a sec. You guys are really just gonna have to bear with me for a second. Just replying to a sort of important text message. I should put music on for you during this. Okay. Okay, now I'm back. All right. Too much stuff here. Keys. And here we go. Yep. Okay, here we go. Now, so this is the third. This is part 3 of Genetic Algorithms tutorial. Great. And I'm gonna have this running. You know what I'm gonna do? Yeah, I'm gonna leave it. Okay. You know what I'm gonna do? I'm gonna just start part 3 by reviewing this algorithm. Then I'm gonna run the code, change some variables in the code. Let me make sure I know where those are. And you know what I'm going to do? This code has all of these comments in it, which are just sort of in my way. And what I want to do is change things like the population max, the mutation rate, yes, and then, hold on, population max, mutation rate, and then in this function is relevant new car. Just curious here. What did I break? Sorry, everybody. Don't break the example. Oh, it's a string? No, why would this not work? Weird. I just wanted to demonstrate something. That's so strange. Whoa. That's so weird. I don't know what. All right, okay, yes, okay. Yes, B100DYH311. Yes, I am assuming no knowledge of this whatsoever. And so far, this is P5JS. And I was just trying to demonstrate a weird idea, which was to show you no variation. What if I did? But I don't know why. Why picking a specific? Why would this not work? It's so. Is there an error? Oh, hold on. Well, how about looking at the console? Cannot read property crossover of undefined. Huh. Okay, I'm. Never mind. I don't need to demonstrate this part. Okay, here we go. This is the algorithm. This is the code. I'm not going to change this part. Never mind. Whoa, hold on. Am I running 9.1? Yes, just to be sure about it. If I change this to 20. Okay, 50. And it was 200. Okay. Sorry, everybody. Here we go. So I want to make little notes of things that I want to make sure I mention that were good questions in the chat. So things that I'm thinking of right now are, couldn't I just pick the right characters? This is an important thing. I want to make sure I talk about improved fitness function. I want to talk about genotype versus phenotype. Those are three things. There were some other questions people asked. Yes, Akash, I did say I will show it in Java as well. Yeah, at the end of this video I will do that, so you can have the Java code for this as well. They're basically the same. So let me get that opened, just so I have that opened. Chapter 9. This is the Java version. It's really the same exact thing. I don't know why this total population is in the wrong place. I kind of want to fix that.
There we go. Okay, so I'll leave that open, and back to here, back to here, back to here. Okay. Okay, everybody. And then this is just things I want to make a note of. And I think, sorry, I think what I'm going to do is erase this. Okay. So I might need to use this at some point. Okay. I really want to change the key mappings to these screens, but I'll do that later. Okay. Here we go. I think I probably cycled this camera like 15 million times. Let me just do it again. And here we go. Okay. Where's my, oh, you can use the black marker this time, it doesn't matter. How are we time-wise? 1 hour, 40 minutes in. We're good, we're good. I'm going to get through a lot of stuff here today. Yes, I agree, Agustina. I agree, Agustina. I can see this as X. I have some sort of like automatic system for cycling the cameras that I just like, I just haven't figured out a better way of doing it. I want to get different cameras. That's, as I start, yes. That's one of my first priorities if I start generating funds. Just to sort of improve some of the equipment here. Okay, here we go. Hello, welcome to part 3 of my genetic algorithms video series. In this video, what I'm going to do is actually look at the algorithm that I described in full in the previous video and find all of the pieces of this algorithm in a code example and explain to you how it works. I'm not going to be programming this example from scratch. I'm using an example that is in the Nature of Code book, from the Nature of Code book itself, but I'm going to tie together a bunch of pieces and cover a whole lot of stuff and show you how things work. So just to remind yourself, or myself, for some reason, I just want to do this again. I apologize to the watchers of the live stream or the archive who now have to listen to me start this video again. I feel like I need to do some like Tai Chi or something. My body feels very stiff. It's just so hot. We need a studio with air conditioning next time, next summer. Okay. Hello, welcome to part 3, the third video in this series about genetic algorithms. In this video, I'm going to just quickly review the algorithm itself that I covered in full detail in the previous video, and then I'm going to open up a code example and look at all the pieces of this algorithm, where they are in code, how the code works, how you can write the code, and answer a bunch of questions that are hopefully on your mind at this very moment if you are here watching these videos. So, if you recall, the problem is to evolve the phrase to be or not to be, that is the question. We start with a random population of phrases, all with random characters. That's the first thing that happens in the program setup. The second thing that happens is to evaluate the fitness of every one of those phrases to calculate how many characters did they get correct. And then the third step is to create a new population of that same number of elements by selecting the members of the population with the highest fitness through some sort of probability mapping that I'll get into the detail of how that works, and generating, I don't know why, I think I suffer from a, I feel like I'm always just repeating myself problem. Yoga. This is the third time's a charm. I think I don't want to just like walk through the algorithm again because I just did that in the previous video. So here we go. One last time. One last time. Hamilton. Anyway, relax. Take a break with me. One last time. Breathe. Okay.
Hello and welcome to part 3 of my genetic algorithms video series thingamabob, the jingamabob thing. So in this video, what I want to do is look at, again, this algorithm that I went over in full detail in the previous video, and actually open up a code example and find all of these steps. Step 1, initialize the population. Step 2, calculate the fitness. Step 3, do reproduction through crossover and mutation. And step 4, replace the original population with the new population. Repeat, 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 repeat. I want to look at that algorithm and find all the pieces of it in code and talk about some of the pitfalls and strategies and different things you might think about when then trying to take this and apply it to your own scenario, your own example. So here's the algorithm. I have it for reference that we could come back to. And first thing I want to do is just run this example. This is running in the browser. This example is programmed in P5.js. I will show you at the end of this video. I'll just run the same thing in processing to show you the Java code as well. And you can see in the talking there, in my talking, it evolved, this system evolved to be or not to be, that is just to be or not to be, period. So one thing you can see in this example is that I'm kind of drawing on the right side here all of the various current elements of the population. And you can see those current elements of the population at this point where the program stops, where one of them is the exact correct phrase. You can see here what they look like, and if I refresh the page, you can see the population itself starting to get closer and closer to that correct phrase, and eventually it's going to stop, and here's just sort of a selection of those members of the population. You can also see over here, I'm kind of having the program always show you the current element of the population with the highest fitness, and you can see that over here, and you can see this is the current element of the population with the highest fitness. Eventually that will be 100% fitness, to be or not to be. And then I'm also showing you how many generations, so this happened in 514 generations. What's the average fitness? Remember, the fitness function calculates the percentage of characters correct from 0 to 100%. How many characters does the phrase have correct? And you can see the average fitness goes up over time. It doesn't get to 100% because when one of the phrases has one of the elements of the population has the correct phrase, the rest of them still don't have the correct phrase. And then also showing you the total population and the mutation rate. So before I get into the code, I even just want to change a couple variables here and show you a little bit about how the system behaves. So for example, what happens if I take this mutation rate and the maximum population and the mutation rate are simply just variables in the code? There's also a target phrase, right? So I could actually just change this program right now to be unicorn. I've never done this. And run it again. We can see how quickly it only took, with a short phrase, only took 5 generations to get unicorn. Come up with your own. I'm going to go back to be or not to be. I'm going to take the mutation rate and make it 0. And now I'm going to run this again. Now notice what's going on. It's kind of sort of settled into something. Look, all the members of the population actually have exactly the same sequence of characters. The best phrase is not changing, and the total generation is just going up and up and up and up and up. So this is a scenario where if there is no mutation, there was not enough variation at the start to actually evolve the phrase, right? There was no initial member of the population with an O as the 1, 2, 3, 4, 5, 6, 7th character. So this is something you really have to be careful of. This mutation is required. Now, one thing I could do is just say, well, the total population was only 200. So I could make the total population 1,000. And look, we actually got to the best phrase, the target phrase, in 44 generations with no mutation. So with a population of 1,000 elements, there is actually plenty of variation. You know, we can see what happens, by the way. I have no idea if I just have a population of 1. Well, that kind of broke it. Let's give it a population of 2. That broke it also. 10. Right? You can see, oh, this, I love this. This page is in Norwegian. That's how to use it. So with only 2 members of the population, we got a phrase that's in Norwegian. Okay, so you can see how the size of the initial population is quite relevant. Now, let's talk about something here that's kind of important little factor also. Let's go back to that population of 1,000. We can see I was able to evolve the correct phrase in 41 generations very quickly. Now let me make a population max of 5,000. 27 generations, even more quickly. Let me give it a little bit of mutation, 1% mutation rate. It took longer that time, but this is sort of randomly. I'm getting it rather, there's a loud noise there. I'm getting it rather quickly. One thing I should mention here is you have to remember this is an artificial problem that I've designed to demonstrate a genetic algorithm. I'm not actually trying to get to be or not to be the fastest, because I could do all sorts of things like, okay, I know what the answer is, so when a member of the population has the correct character, I could actually just use that correct character and make sure I put that in the next year. There's all sorts of things I could do to actually try to get to the answer more efficiently, like just say print line to be or not to be. But what we want to do here is just sort of look at how does the genetic algorithm behave and perform, changing some of these variables. But I kind of got off track there, and I sort of meant to talk about that later, but whatever, it's fine. Here's the thing. I could keep ramping up the population max, thinking it's going to be faster and faster. And now I have a population max of 15,000 characters. And you can see that I was able to get to be or not to be in 30 generations. But look how slow the kind of frame rate, so to speak, of each generation. The program starts to run slower and slower and slower. Like if I were to have 100,000 members of the population, I think I might have just crashed. I've practically crashed the browser here. Like I might be able, it's running so slow. So there's a trade-off here. Having a large population helps because you have a larger pool to start with in terms of variation. But once your population is so large, the computation can become rather slow that it just takes forever to get there. So even though I might have gotten there in 25 generations, it took much longer than if I just said 1,000 members of the population, which you can actually crunch through really, really fast. Might take more generations, but actually happens faster. So that's another important thing. That's another important thing for me to mention. Another thing that I should mention here is that the mutation rate itself, boy, I haven't started looking at the code yet. The mutation rate itself is also a prime key factor. You know, more mutation you think might help. But what if I say 0.1, like 10% mutation? If the mutation rate is so high that there's mutations happening so often, it's almost akin back to that brute force solution where everything's just random in the first place. For example, at 50%, everything becomes almost completely unrecognizable in the sort of like list of the population. And if I were to make the mutation rate 100%, this is actually complete and total randomness. Okay, pause for a second here. So what I realized I just did right now is instead of actually looking at the code, I just sort of ran the example. And tweaked a bunch of the variables. Sorry, I was like feeling a little faint there. I need to drink some water. So I think maybe what I'm actually going to do is wrap up that as its own little standalone video. I know I used the word akin. I do read the live chat, Red Leaf Studios, but I'm not catching everything, but I glance over it as much as I can. I think I'm going to just say a couple sentences to wrap that one up, and then actually look at the code in the next video. Okay. It's very hot. Okay. All right. Okay. I realized what I actually did in this video was kind of talk about some of the parameters of the genetic algorithm, tweaking them and how that affects the genetic algorithm's behavior. So I'm actually going to wrap up this video that just kind of, I've said the incorrect things at the beginning, and then actually you can get to the next video. Maybe I should re-record, maybe I should re-record the beginning. This is kind of silly what I'm doing here. I don't know if Mathieu is watching to give me any advice here if this is crazy. I'm going to, in case it's possible, I'm going to re-record a beginning of this video, and then which says instead of saying that I'm going to look at the code, that I'm going to run the example and look at tweaking some of the parameters. Boy, I'm really overdoing it here with the sort of post-production required, but yeah. No, I know you want I know B100. You want me to move a little faster here. I hear you. I'm getting there. Okay. So this will just take me 5 seconds, and maybe it'll go in there, maybe it won't. Okay. So I'm going to record a beginning, and then an end, and maybe it can get spliced together, maybe it can't. Whatever. I'll figure that out later. Um, okay. I don't remember what. Okay. I don't know if this is possible. Just try it. Hello, welcome to part 3 of my genetic algorithms video series. In this video, I am going to review the. Actually, no, I'm not. Help! Okay. Oh, I'm using numbers? Is that what I'm using? Tolka? Okay. Okay. Hello and welcome to part 3 of my genetic algorithms video series. I'm almost ready to dive in and actually start looking at all the pieces of the code and how they implement the actual genetic algorithm itself. But what I want to do in this example, you can see the genetic algorithm just ran and it arrived at the phrase to be or not to be. What I want to do is just kind of run this example a bunch of times while tweaking various parameters of the system and look at kind of what all the pieces here of the example running are. Okay, and then I think that can get edited to the next thing I do is kind of zoom over, refresh, and start saying what these are and that sort of thing. So we'll see if that happens. Now I'm just going to do the end. And I'm going to go back to, we'll see if this can be edited together. Someone's asking me about Library of Babel website. I have not. Maybe I have, maybe I haven't. I'm not sure. It's not ringing a bell for me right now. Okay, so thanks for watching this particular video. In the next video, I'm actually going to peel open, pull open, whatever. There's I'm going to open a suitcase or pull a curtain, something, and actually look at the code itself. Go back to this algorithm. What are the pieces of this algorithm, and where are those pieces in code, and how are the different techniques working to make this algorithm run? Okay, so Mathieu, thank you. I think basically there's a little beginning, there's the looking at the parameters, then there's a little end, and now I'm going to kind of do the next video, hopefully without stopping and starting, where I actually look at the code itself, matching it with this algorithm. And, okay. Why does your desktop use huge file icons? You know, at one point I made them big for visibility, and maybe that's completely unnecessary and I should shrink them again. I am going to get another glass of water, and then I will come back.
Coding rainbow.
Oops, wrong. Be right back. Okay, I am back. Okay. One moment, please. Okay, here we go. Just getting set up here. One on the bottom is the JavaScript one. I just want to So I'm going to cover what the pieces of the code are and that sort of thing. Okay. 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 Here we finally go. Hello, welcome to part 4 of this ongoing video series about genetic algorithms, and we're really finally ready. I am ready. I am here with you, excited to take a look at this algorithm now in code, in both JavaScript and also as well in Java. I'm going to look at 2 different examples. We're going to look at all of the pieces of the algorithm. What does it mean? How does step 1 work? How do you create that initial population of elements? How does step 2 work? How do you calculate the fitness for every element of the population? How does step 3 work? How do you use probability to pick the parents? How do you write code to implement crossover and mutation? And then step 4, how do you take that new population, make it the current population, and repeat? So I want to look at all of those pieces in code. And so the first thing I want to mention is in the example, and I have the example already written, so I'm not going to be writing it from scratch this time, but rather I'm going to highlight the different pieces. And of course, in this video's description, you can find a link to the code itself. But the first thing I want to mention is that there are actually 3 different JavaScript files where the pieces of the code are. There's sketch.js, which has the main sort of algorithm being implemented, where setup and draw, I'm using the P5JS framework, setup being the things that happen at the beginning, draw being what loops over and over it again. DNA.js is the code where all of the functionality of the DNA object is stored, this DNA object that's actually holding that phrase itself. So I'll get into that. And then there's a population.js file. That population.js file is the JavaScript file that holds a population object. And the population object contains an array, a list of all of the DNA objects. The population, each element being an individual instance of this digital DNA. So this is how the code overall is organized. And now I'm going to start looking at individual pieces. Okay, so the first step here, step 1, is create a population of n elements, each with randomly generated DNA. So let's look at how this works. The first thing I want to mention is that I do have a variable called popmax. That's where I'm keeping sort of track of what is the max, what is that n, what are the n elements. And you can see that is assigned here in setup as popmax equals 200, right over there. Now, the population object is where I actually say this. Actually, I want to make this a little bit wider. Apologies. Come on. Interface. What? Timeout. I'm having a problem here. What is my crazy computer doing? Make this. What sort of weird Have I returned? Am I live on the Facebook, the Twitch, the YouTubes? Great. Let me know if the sound and everything seems fine, if things are back and working. We don't have any more moments, and we could have more. Moments. Okay. Everything good? Okay. All right. So I feel exhausted, but I have my magic invisible glass. And is my mic? Is everything okay? People are asking still questions in the chat. Everyone says all okay, all okay. Okay. All right. So, where was I? Oh, did I get anywhere in that video? I guess I just need to start that one over because the mic stopped working in the middle of it. Okay. Right? I just need to go back to this, and then this, and then this, and then this. Okay. Was there enough there, Mathieu, was there enough there that I should just pick up from where I was, or should I go back to the beginning? Problem is you guys are like 15 seconds behind me in the chat, so I could ask a question and then I have to wait 20 seconds. So that when you answer it, then you have to wait 20 seconds because you watch me waiting 20 seconds. I should restart. Okay, great. Thank you for the answer. Oh wait, it's back. Okay. Let's hope everything works well. Okay. Back to life. Back to reality. Okay. Why is this not finishing? Go back to the beginning. Okay, here we go. Welcome to part 4. Welcome to part 4. Okay. Yeah. Hello. Please, everything work. I'm kind of an atheist, but I'm going to pretend that I'm praying or something. Okay, anyway. Hello, welcome to part 4 of this video series thing that I'm doing about genetic algorithms. Okay, what's going to happen now? In this particular video, what I want to do is actually finally, I know it's taken me 4 videos, look at the code itself. So I have a pre-made code example, as you know. I'm not going to write it from scratch. It's coming from the Nature of Code, Chapter 9. You can find the link to the chapter and the code in this video's description. But what I'm going to do is look at the algorithm itself that I covered in detail a couple videos ago and look at where all of those pieces are. So what does it mean to initialize a population randomly? What does it mean to do step 2, selection, to calculate the fitness of every member of that population? How do you write a function in code to actually do that? How do you write a function to pick randomly, but have each thing that you're picking randomly have some sort of higher or lower probability of being picked? That's a kind of a tricky problem. We'll look at how is that solved. And then how do you do this thing heredity? How do you do crossover? How do you write the algorithm for crossover? How do you write the algorithm for mutation? And then have this new population that you then make the current population repeat over and over again. So I want to look at every single one of these steps and find in the code where those steps happen. So let's just start doing that. Okay, actually, before I do that, though, let me at least open up this directory here and show you that how I have the code organized. So I have the code organized. You know, there's the libraries folder for the P5JS JavaScript library I'm using. There's the HTML file, which references the JavaScript files. And there's some like kind of worthless styling in style.css. But the files that actually matter to you are sketch.js. That's where kind of the main program is. Setup, this initialization state is. Draw, this looping state is. That population.js, that's an object that manages the array of all the elements of the population. So there's functions for calculating the fitness values there. There's functions for doing the selection there. And then there's the DNA.js file. This is a really important file because this file is actually, this object, this DNA object, as I look at more sophisticated examples in future videos, the code in DNA.js will actually be present in almost all of them. So a lot of what's great, even though this example is kind of completely trivial example, because again, I could just type to be or not to be, that is the question. The code in this example can actually be almost lifted essentially verbatim to other scenarios to write your own genetic algorithm. And that's kind of the next video after this one that I'll get to. How do you take this code and implement it in a different scenario yourself? But so the DNA.js has that DNA object. It has a function for mutation. It stores the characters for each phrase, that sort of thing. It's each individual element of the population. Okay, so let's go back to the algorithm. Step 1, create a population of n elements. So let's go to the code. And where this happens is actually in population.js. And we can actually see this happen right here. I say create population equals a new population. So the population is made with 3 arguments. A target, which is the target phrase, to be or not to be, which I could change, a mutation rate, and a population max. So those values are sort of stored also in that population object. And in the population object itself, this is the kind of key variable, this dot population. Oh, no. Don't forget this dot. So variables that are part of that object itself are attached to it by saying this dot population. So this is a constructor function that's creating a JavaScript object, and a population is made as an empty array, and then there are a certain number of elements of the population made as DNA objects. So I think if I come over here for a second, the population object itself is just a big array of n elements, and each one of those elements is a random phrase. You know, popcorn, you know, unijorm, whatever these sort of weird nonsense, you know, whatever. Each one of the members of the population is a random phrase, but it's not just a string. So rather than use just a kind of literal string, what I'm actually doing is creating a DNA object, and this is kind of crucial. And this is now where the DNA.js file comes in. DNA.js has an object itself, which is an array, called this.genes. So if I come back over here, whoops, step on a light, on a fan. I think I broke, no, I didn't break this. Anyway, that light went off. This might be a little bit darker for a second. I'm back, hello, everything's okay. The fan is blowing up my legs. So this is the population array. Each element of the array is a phrase, which is actually a DNA object, which itself is an array, and each element of that array being a single character. Okay, so that's how each element of the population is an array of elements. Each element is an array of characters. So this is ultimately how let me come over here. This is ultimately how that population is made. Make a certain number of DNA objects. Each DNA object, each element is a new car. Now, one thing that's a little bit goofy here is I wrote an entire function to make a random character. There might be an easier way to do this in JavaScript, but I really just want random characters. I'm using that sort of ASCII table here. So I'm picking a random number between 63 and 122, and then converting those from that number to a string using its character code. So like using the ASCII table. And if you're not sure what the ASCII table is, I'll try to include a reference, a link in this video's description to that. So that is step 1, initialize. Okay. Step 2 being selection. Now we need to evaluate the fitness of every element of the population. So where does that happen? So one thing, by the way, that I think is worth looking at is this main program, right? So draw, by the way, look at this. The draw function essentially, and it's funny how I'm doing this in a slightly weird order. Maybe I should flip this around. But what the population does, the population object itself has all of these steps of the algorithm written in as specific functions. So I could just say population, calculate the fitness of every element. Population, perform natural selection. Population, generate the next population. And then population.evaluate, what that function does actually is just sort of checks to see if we're done. So these are the three. I don't know why I did this. I'm going to just right now put this first. Because it's looping over and over again, it doesn't necessarily matter. But I'm going to calculate the fitness first, because this is sort of essentially the order of the genetic algorithm itself. So this is step 2 right here, selection, which calls that function calculate fitness, which is right here. Uh-oh, I froze. Hopefully I didn't actually object. Somebody in the chat will tell me if this stopped working. There's this function, calculate fitness. And notice what that function does. It loops through every single member of the population and calls another function, calc fitness. So when I say calc fitness on the population, really what I'm just doing is saying loop through the entire population and call a function on every element called calc fitness and check the fitness against that target phrase. So now if I go into the DNA object, we can see calc fitness right here. This is now a key function in any genetic algorithm is the fitness function itself. So you can see what's going on here. I start with a score of 0. I iterate over every single character in the phrase. If the particular character in the genes array matches the character in the target phrase, increase that score by 1, and the fitness is the score divided by the total length. So the number of characters correct divided by the total length gives you a percentage. I got 9 out of 10 characters correct, a fitness score of 90%. So you can see that's what's happening, and so that's step 2, selection, calculate fitness. Initialize, generate 200 random DNA objects. Step 2, calculate the fitness for those random DNA objects. Okay, now the next thing we need to do is reproduction. Now here's the thing. Let's come back over here and talk about how this is going to work. So let me erase this for a second. So if you recall, I had this idea of this spinning wheel of fortune. So here's the wheel. Maybe there are, a whole bunch of members of the population, each with a certain fitness, and depending on their fitness, they get a bigger slice of that pie. And then the idea is you spin this wheel and you pick a parent and pick another parent. Well, I could actually build in the code like this sort of physics simulation of a spinning wheel, but that would be a little bit overkill. There are a lot of different techniques of picking random elements from an array based on probabilities. There's this technique where I can pick 2 random numbers, a kind of qualifying random number. I forget what I called it. I actually just recently made a video or an example about this, accept, reject kind of algorithm. But the algorithm that I'm going to use is actually a very simple technique that works well in this case. So let's say I have A, B, C, and D. And I want A to have a 40%, A has a 40% chance of being picked. B has a 20%. C has a 15%. Oh, why did I make the math so hard on myself? 60, 75. No, I don't. This is not going to turn out well for anybody with 15%. So we'll just make, we'll make C 10%, 40, 60, 70, and D 30%. Okay? Now, look at this. Let's say I have an array. This is the array. And the array looks like this. A, B, C, and D. Let's say I want to pick a random element from that array. A, B, C, or D. Each element has an index, 0, 1, 2, or 3. So I could pick a random number between 0 and 4, but not including 4. Each one of these has a 25% chance being picked. I have a 1 out of 4 chance, I can't write 25%, of picking any of those. What if, however, I were to write the array a different way? So I'm going to write the array like this. A, B, B, C, D, D, D. Notice I put A in that array 4 times. I put B in that array 2 times, C in that array 1 time, and D in that array 3 times. Now, there are 10 elements of the array, 4 of which are A. So if I pick a random value between 0 and 10, not including 10, 0 and 9, right? 4 out of 10 times, I'm going to pick 0, 1, 2, or 3, an A. 2 out of 10 times, I'm going to pick a 4 or a 5, a B. So what I can actually do, if I have this is the population array. That's the actual population array in the code. I build another array, which I think I'm calling a mating pool. Or I might call it like Darwin or something, where I take these elements and put them in this array a certain number of times according to their fitness. So the more times something is in an array, the more likely it is to be picked. And I think, if I come back over here for a second, I think I have, so this is kind of just some other diagrams demonstrating this idea, right? What if I have all of these elements with a different probability? This is the spinning the wheel approach. But what if instead I just create this big bucket and I put like A in there so many times, B in there so many times, C in there, and then I pick out of it. The more something is in the bucket, the higher the likelihood is that it will get picked. So how do you do this in code? If I go back to the code, again, we're looking now for this function, natural selection, which says generate a mating pool. So let's go look in population, and here it is. Notice what I do. This dot mating pool is now a new empty array. And then ultimately later on, right down here, there is this code where I'm adding every member of the population into the mating pool n times. So how do I figure out what that number n should be? Well, this could probably use some refinement, and there's different ways you could do it. But ultimately up here, what I'm doing is finding out, okay, what's the member of the population with the most fitness, the highest fitness value. Then what I do is I take that particular element's fitness and give it a number between 0 and 1, mapped from 0 to maximum fitness. So in other words, what I'm saying is I'm doing a sort of step where I'm normalizing all these fitness values. Now, ultimately, I kind of made up an example here with sort of pre-normalized value, like 0.4, 0.2, 0.1, 0.3. But your fitness scores might just be like a whole lot of numbers. Like this one got a fitness of 2,000. This one got a fitness of 3. This one got a fitness of 4,228. So what I do is I have a way of saying whatever the fitness numbers might be, take them all and just have them have a range between 0 and 1. And actually the next thing I do is multiply it by 100. So actually the range is between 0 and 100. And you can see that's what's happening right here. I do that mapping. Then, I lost control of my computer. And then I multiply that value by 100, and that's n. That's how many times those elements are in the mating pool itself. So if I were to just do something which I'm a little bit afraid to do, but I'm going to say console log this dot mating pool, and I'm going to go back to the sketch and run it. And what you can see is these are the mating pools, right? And it finished, and you can see that there are this array. This array is actually quite huge. I wanted to say this dot. I think it might make more sense to say this dot mating pool dot length. So you can see this is how many things are in the mating pool, in the 15 to 20,000 range, whereas the population itself is just 200. But based on their fitness, that mating pool is built much larger. Okay, so we're getting there. That is, let me go back to this particular algorithm. So that is selection. So once I have the mating pool, then I'm ready for step 3, reproduction. All I need to do is I have the mating pool. All the probabilities are already sort of built into that big array right now. I just need to pick 2 random ones from the array. And we can go into the code itself, and we can see where that happens. Look at this. I want to do this n times. I want to make a new population. Here are all the steps. That's the generate function. Pick 2 parents. Give me a random index into the mating pool, A. Give me another random index into the mating pool. Now, technically speaking, you might want to say to yourself, do you know what? If B equals A, I want to invalidate B and pick another one. But me, I'm sort of being loosey-goosey about this. It doesn't really matter if I, by accident, on the rare occasion, pick the same parent twice. Big deal. So I have two parents. I play partner A and partner B. Both of those are DNA objects that come from the mating pool. And then I simply call crossover. I take partner A, crossover with partner B, and that is a new child element. And then child, I call mutate for the mutation rate. And then I have that new member of the population. So this happens n times. I just say I have the mating pool, give me two parents, cross them over, apply mutation, here's the new child, it goes into the population. This happens over and over again. So I've really looked at every single element of this algorithm here. The last thing, though, is we could look at what has actually happened in crossover and mutation. So again, just to remind ourselves, this is the crossover step. The technique that I happen to be applying is take half of one and half of the other and put them together. But certainly you could take one from each one. I don't think I have a diagram for that, or you could do it a different way. And then mutation, I'm using this probability to say at any given random there's a certain chance that I might just change that character randomly. So let's look at how those functions work. Now notice, where is that function happening? I'm saying partner A, that's a DNA object, crossover with partner B, that's another DNA object. So that code for the crossover function itself is in this DNA object, which is right here. So look at this. This is now the crossover function. First of all, I'm creating a new DNA object with the same length, the same amount of genes as this current DNA object. I'm picking a random midpoint, right? I could just say, the midpoint is always 5, or the midpoint is always this.genes.length divided by 2, but I'm picking a random midpoint, and look at this. This child's genes are either coming from, right? If I'm on one side of the midpoint, they come from this particular DNA object's genes. Otherwise, they come from the partner's genes. So this is how I'm applying crossover. It's literally just a new array, take elements from one array or from the other array. And then mutation, you can see here, mutation, these are incredibly simple functions. Then I have a new child DNA object. And mutation, these are incredibly simple functions. All it is, hey, let's look at every single gene and just say, pick a random number between 0 and 1. If the mutation rate is 0.01 or 1%, if I happen to pick a random number less than 0.01, then just give me a new character. Forget about whatever I got through crossover, give me a new character, okay? So this is it. These are all of those pieces. This is the main program, right? In setup, I have what's the target phrase, what's the maximum population, what's the mutation rate. Then I create a new population object, and then I just walk through the algorithm itself. Calculate the fitness, build the mating pool, generate the next population. Evaluate is just checking to see how everything did at the end. And then there's some other code for sort of displaying all the information using DOM elements and that sort of thing. But this is the key algorithm. It's all in separate functions. And each one of these functions, calculate the fitness, natural selection, and generation, simply iterates over that entire population. Right? The population object has a population array. I'm always iterating over that population array, calculating the fitness for every element of that array, assigning a probability for every element of that array, picking a random parent from that, picking a random element, picking a new child for every element of that array. And all of those functions are in turn in this DNA object. The DNA object stores the actual genetic information. It has a function for calculating the fitness. It has a function for performing crossover, and it has a function for performing mutation. So these are all the elements. So I've kind of finished this here. I'm going to do a follow-up video where I talk about a couple things that I think could optimize or change the way this works. But ultimately what the project for you in your head that you want to think about for right now is, well, what is the thing that you want to make that you might want to try to evolve? Are you trying to evolve a particular design to make it more beautiful or more intuitive? Are you trying to evolve a particular animation behavior of an element on the screen? And what might be, how could this algorithm apply to your scenario? What might be the genetic information? How is I just made this weird closing my one eye thing expression at you. I don't know why, but how can you apply this sort of algorithm and idea to your particular creative project. And that's what I'm going to start to get to as I look at a few more advanced, or advanced is the wrong word, but really more sophisticated examples of applying this. So I'll see you in the next few videos where I look at some other scenarios and other things with genetic algorithms. Okay, bye-bye. Okay. Oh my God, I'm dying of heat stroke in here. How am I doing, everybody? It is now, oh, I have to look at the time. It is 1:09. Oh, I have only had till 1:30. Oh boy. Not going to finish this today. I meant to actually have the whole day, and I was just going to take the whole day to do this, but I have a very good excuse, which is that my son is actually doing a tech camp this week where they're learning Scratch programming, and at 3 o'clock today, actually I have to be there at like 2:30 or 2:45, they're doing a showcase of all the kids' work, and the kids are ages between like 7 and 10. So I'm going to go check that out this afternoon, which I'm very excited to see all these coding projects made by kids. But I'm not leaving just yet. I think I have time to do one or two more. The other thing is just so hot that I do sort of need more of a break. Okay, how's everybody doing? I'm losing steam a little bit here.
Coding rainbow.
Cutting rainbow. Cutting power.
Okay, thank you for your nice comments. All right, so let's think about this, where I am. I'm going to go to GitHub here. So I want to edit this. I have done the overview, the core algorithm, Shakespeare Monkey problem demonstration. So the things that I want to cover are, okay. I'm going to call this make it your own. Okay. Yeah. So, okay. So this is my outline. Tarkish asks, how do I get the example? All the examples are, if you Google nature of code, you'll find the nature of code website, and everything is in chapter 9. And there's a link to the GitHub repository with all the examples and that sort of thing. Recent purchases. Apparently I purchased this recently, and Google is telling me that. What? I only have a 4.6 out of 5 on Goodreads? Come on. I think that's probably pretty good, actually. I'm going to go, you guys won't be able to see me, but I'm sitting down in front of this fan for a second. Cool off. Can you hear my voice in the fan? Okay. Yeah, the Raspberry Blonde asks about using a genetic algorithm to match colors. I think that's a really super interesting idea. Where was this? This is a cool project from 2008, I believe. Okay, so I think what I'm going to do is at least, wait, I need to leave here by 2. And it takes me like 15 minutes to get cleaned up and everything, turn stuff off. So as long as I'm stopping the live stream by 1:45, that's good. So I have about a half an hour left. You guys help me watch the time. And what I want to do in the next video is talk about Um,
Coding
oh, whoops.
power.
Oh, this camera's off. What I want to do, I'm going to erase this, is look at the Boxcar 2D, look at the Mona Lisa example, and then open up my, oh, I didn't show the Java code at the end of that video. Whatever, I can make that an addendum. Well, but I don't know if that matters so much. If people in the chat want to tell me that I really should just do a quick 2-minute, just open up the Java code to tack that onto the end of that video, I would be glad to do that. I want to look at, let me erase the rest of this, I guess. Okay, the Mona Lisa example. I want to look at the Boxcar 2D example. And then I want to look at my path generation example. Yay, addendum. Okay. Yeah, let me do the addendum real quick. This is it, right? Oops, I'm in the wrong screen. Okay. All right, I'm going to do this real quick. We'll see if it's worth adding in. Okay. Okay. Quick addendum here, since I said I would do this. For those of you that are interested, the code for this example is also available in the processing programming environment, which is a creative coding environment built on top of the Java programming language. So if you're looking for Java classes to do a genetic algorithm, you can find those as well. And really, ultimately, it's all kind of the same. There's some, little differences. We've got this sort of more classical object-oriented programming where I have a DNA class and a population class. The population itself is an array, but one thing you'll notice that's kind of key is the mating pool I'm using as an array list. In JavaScript, arrays can easily just kind of be resized and things can be added and deleted just with a regular array, but in Java itself, an array is a fixed size, which works for the population, which always has a fixed size, but the mating pool itself has to have a flexibly sized array list. But otherwise, everything is essentially the same, and you can see here I have setup, where I'm creating a population object, and draw, where these functions are being called. Natural selection, generate, calculate fitness, and various things like displaying the info by drawing text of what's going on the screen itself. So look for the links in this video's description for also the Java code, and if you have questions about that, please let me know. Thanks. Okay. Great. So that I did. That's done. I'm picking my nose. So I was watching back one of my videos the other day. I noticed I was like scratching my armpit. I'm always doing weird things that I probably shouldn't be doing live on camera. Okay, so don't save that. Don't save this. Okay. Okay, now I'm going to go to, the Mona Lisa. Roger, what do you guys think? Is it Johansson? Anybody know what you would guess? Somebody in the chat can let me know. So I got this going. And then smart rockets. Ooh, shoot. This is broken. Hold on, everybody. If somebody could watch what I'm doing to fix this and file a GitHub issue or a pull request to also fix it in the repository. I'm looking at NOC 903. I like how someone told me how to pronounce Johansson by just retyping the name. Is it Joe with a J sound or Y sound like Johansson? And then line 68 of rocket.js. Huh. This dot position.
Why is this not working? Oh, I don't want to. New population. Create vector. Shoot. Sorry, everybody. Shoot, there's a not working. Cannot read property X of undefined. Line 68. Comment this stuff out. Johansson, thank you. This dot's on. Yeah, could that be it?
This dot, this dot, this dot, this dot's on.
I have the this dot position. Is position the variable name? Yes. Let's see what's going on here. Whoa. Somehow this, okay, this is not even being called. Shoot, this is taking up a lot of time. Num. How is this not being called? Am I looking? Oh, I'm looking at the wrong code. Ugh. Sorry. It would really help for me to look at the right code. Target. Yeah, there we go. It was not this dot, but
This dot, this dot, this dot, this dot's on.
okay, so I fixed that. Okay. Sorry, everybody. Okay, so now I've got to get back to what I was intending to do. Close up all these smart rockets. I think I can get rid of that. This. Okay. All right, so I've got a 123. Here we go. Let me cycle. Let me try to get through another bit of content here. And see how we do. All right. Yeah. I'm going to say Johansson. And maybe I'll get it wrong, but that's what I'm going to say. Okay. All right, here we go. Sorry. Okay, this is the 5th video. Wonder how many steps I have doing this. My Pebble Watch tells me I have 10,000 steps today. Just I think walking back and forth like this. And also dancing to
This dot, this dot, this dot, this dot's on.
okay. All right, here we go. Got to get this done. Got to get one more little lesson in here. Okay. Maybe I just need to shave my beard because it's just so hot and heat's being trapped in. I'm a little bit hungry. Feel a little faint. A little sweaty. Okay. Here we go. Number 5? Okay. Okay.
You're back. That's nice of you to come back. I'm now in the 5th video here. And in this video, what I want to talk about is, okay, so we have this idea of a genetic algorithm, right? I have the algorithm itself. We talked about that at great length. I talked about how you can implement that algorithm in code. I looked at this sort of DNA object and population object. But the example was still just this kind of trivial example that just sort of demonstrates that the algorithm works by having a known result, starting with randomness and arriving at that known result. What you want to do is have something more interesting where you might want to evolve a particular design or a particular animation behavior or something else a piece of music, something that I can't even think of right now that's creatively in your head. So what I want to do in this particular video is talk about what are the pieces of that genetic algorithm that you can just copy from my code exactly every single time you use it, and what are the places where you need to sort of interject and come up with your own creative solution to the particular aspect of the code. So let's look at a few examples of different scenarios. I showed you this boxcar 2D example. This is in a way like evaluating the design of a physics element in a system through an evolutionary process. And you can see here, this is perhaps not the car that you would design manually, but it seems to be driving itself quite quickly through the genetic algorithm. So what are the pieces of this? What's the fitness function here? And how do you take this car and encode its design in DNA? Those are the 2 essential questions, by the way. Another example that I found here is by Roger Johansson. I don't know if I'm pronouncing that correctly, but somebody correct me on the internet if I'm not. This is very similar to the to be or not to be example, but instead of starting with kind of like random polygons, instead of arriving at a target phrase, this is starting to arrive at a target image through polygons, and you can see after a whole bunch of generations, what is that target image but the painting of the Mona Lisa? So you might think about, okay, well, this actually is almost identical to my to be or not to be example, but instead there's like pieces of the DNA or colors and polygons and positions, vector information. What is that? How do you make that work? And then I'll show you there's an FAQ. There's some other links here you can look at yourself. And then I'll show you one of my examples, which I have running here in the background. This is actually a path-finding example. So what you can see here is there are something like 1,000 little agents moving around the screen. If you've watched my videos on steering behaviors, these agents are actually following a flow field. I believe if I press this button, I can sort of make that flow field visible. This is the DNA of each object. This is what it's in its brain, a grid of vectors around the screen. And ultimately, they're evolving what is the fastest path from the left-hand side of the screen to the right-hand side of the screen. But this example is a bit more sophisticated. I can actually draw some obstacles here. And these elements will actually start to evolve a path around the obstacle. And so I'll come back to this later and see where it's gotten to, how far it's gotten, how good the evolution sort of is. But what I want to do is kind of stop. I've shown you these 3 examples. Maybe you have an idea in your head. What are the things you really, really need to think about? So I want to pause, edit point. I didn't want to close the this thing that has the slide. I'm going to open that back up. Just get this situated correctly. I froze myself in place because I want to get back to this slide. Where was I? Ooh, it's running so slow. Probably because I have all this stuff running. Close this. Yeah, come back to this in a second. Why is it running so slow? Stuff is running on the computer, but I'm like freezing, like I want to stay in the same position. Okay, I'm going to come back to this. It was like zoomed in or something. I don't know what was behind it. Whatever. Doesn't matter. Time. 13:28, 19 created the zombie triangle. Am I running out of time? No, I'm okay. I got 15 more minutes. I'm going to finish this video. I don't know why this is running so unbelievably slow, but I'm not going to worry about that because I don't have time to worry about that. Okay. Okay. So let me return. Okay, wait, hold on. This is me now going back into this is for poor Mathieu. Thankfully, who's going to figure out how to splice these 2 sections together. So looking back at the actual genetic algorithm here, I want to talk about two key places where you really need to interject your own creative spin on this algorithm. Everything else can largely remain exactly the same in any example, in any project that you're doing with the genetic algorithm. So let me come over here and kind of write these out. So number one is the fitness function. The fitness function that I had in the to be or not to be example was counting the number of correct characters. That's not going to work for the boxcar 2D example. That's not going to work for that Mona Lisa example. That's not going to work for my evolving a path with a flow field example, right? You need to think about your particular project. What is the fitness function? Is the music in tune or out of tune? Does the steering agent make it to the target quickly or slowly? Does the thing run into an obstacle, yes or no? Does the image look like the Mona Lisa, yes or no? So you need to come up with your own way of scoring each element of the population. You need to write your own fitness function. That's really key. The other key thing is, I'm going to say, how do you encode your DNA? This is really, really key. And what this brings up is this idea of genotype versus phenotype, right? This is a key concept from genetics that we can kind of have a very sort of simplistic view of here in the genetic algorithm that we're working with. So the genotype being the data itself or the encoding. The phenotype being the expression of that data. The manifestation of it, the visualization, the actual animation of it. And we were sort of spoiled by our example. The to be or not to be example, right? Here is the encoding of my random phrase. You know, unicorn. Oh, really it is an array of characters. UNICORN. That's the encoding. Here's the expression of it. Unicorn. Right? That's the expression. It's the same thing. But in any of these other examples, right, if I go back to this, pause. Mona Lisa genetic algorithm. If I go back to this hold on. If I go back to this Mona Lisa example, you know, the encoding might be a series of an array of polygon objects, each polygon object having an array of vertices. It could be a giant array of RGB A values for pixel colors, and then the expression is drawing it or animating it on the screen. Same thing here with the boxcar 2D. Like, how do you design that car? Oh my goodness, you have to have some type of node-based map to talk about how the different pieces of the car like fit together. That's the encoding. The expression is the thing actually moving. And in this particular example, you can see, by the way, how far it's come. The objects have kind of evolved this flow field around these obstacles. I could make it harder for them by adding some more obstacles. But the encoding, the phenotype is the expression, the movement of these objects through the flow field. But what's the actual encoding? It's an array of vectors. So the first example that I want to actually look at and see how this applies in actual code is an example called Smart Rockets. This is actually based on an example made by Jer Thorpe many years ago, a Flash example on the web. I don't know if I can dig it up right now, but I'll include a link to it in this video's description. But and it's simpler. This one is running in processing. I'll leave this open. Actually, let's make it really hard. Let's draw some more obstacles. See if it can solve it anyway. That's going to be hard. I'm going to go back to the browser, close this. You can see this is a version of this example working. It's quite a bit simpler. You can see that these objects, boy, they're not doing very well, are trying to find a path to make it from the bottom of the window to the top. And it hasn't been running for very long, so they haven't done a very good job of it yet. So this is the same sort of problem as to be or not to be the question. Think of the number of possible paths there are from the bottom of the window to the top. An unfathomable amount. There's a lot of pixels, a lot of ways they could move. So we're trying to search for the optimized fastest path and not running into that obstacle. So what's interesting about looking at the code for this, right? So let's think about this. Let me come back to the whiteboard for a second. So the fitness function. Let's first think about the fitness function. My fitness function, this is the target. This is where they start. The fitness of each one of these rockets is the inverse distance. So to the target that it gets to at the end of its life. So the closer it gets to the target, the higher the fitness. So we calculate the distance between the target and the object, and then I say 1 divided by that distance. That's a way of calculating a fitness function. So that's a specific thing I had to invent for this. Again, there's lots of ways I could improve that fitness function, which I'd like to discuss, but that's a basic idea. So that's one thing. Then this idea of genotype versus phenotype. So if I come back over here, one thing that's really interesting to see if I go to the code, right? Look at this. Here's a DNA object. It is exactly the same. Look at this crossover function. It's exactly the same as the Shakespeare example. Look at this mutate function. It's basically exactly the same as the Shakespeare example. There's this idea of a genes array, which is exactly the same. Everything is the same. Here's the one thing that's different. What goes in the genes array? Instead of picking a random character, I'm picking a random vector. So what each one of those rockets has is an array of vectors. That's like an array of forces that cause it to move around the screen. You can essentially think of it as like if the driver of the rocket has like this control panel where they can like press thrusters with a certain amount of force in a certain direction. That's what they're doing over and over again, and the encoding of that rocket is the sequence of those thrusters, those forces to drive it around the screen. So what's interesting about this is this DNA object, if you look at the code between this, it's entirely the same. The difference is the genotype itself is no longer characters, it's vectors. So it might be floating point numbers, it might be characters, it might be vectors, it might be pixels, it might be polygons. It's up to you to think of what is that encoding of the thing you're trying to express. And in this case, it simply is vectors. Now, the expression of that happens in population because the population, it happens in the rocket object. So this is what was missing, right? In my Shakespeare Monkey example, there was simply a DNA object. That DNA object had both the genotype, the encoding of unicorn, and the phenotype, the expression of unicorn in it. I didn't need a separate object. But in this example, the encoding, the DNA, is vectors, and the expression is the rocket object. And the rocket object, if I come over here, is a physics object. It's an object that has acceleration, velocity, and position. And guess what? It has the DNA built into it, and when I run it, look at this. This is the expression. There's a lot going on in this example, but the expression is go and look at its DNA and apply something from its DNA, the next sequence gene, as a force. So that's the expression. Take the vector and turn it into a force in the physics engine. So I would encourage you to go back and review my forces and vectors tutorial as well as my steering behaviors tutorials, because this example, this is essentially a vehicle object that has a physics engine built into it, but it's how it moves is according to its genetic information. And then you'll also notice that fitness function is right here in the rocket itself. So instead of, and I want to just make this wider so we can sort of see this for full fitness function for a second. Now I did say that distance, the fitness function is 1 divided by distance, but I'm doing a bunch of things in this, in the fitness function. I'm also checking to see if it hit an obstacle. I'm going to do a separate video about improving fitness functions, but I'm adding some extra math to the fitness function to make it a little bit stronger. And I'm going to cover that actually, I think, just separately in the next video. I'm going to make a note of that to do that. So you can come back and I'll talk through that. But you can see here, there's lots of stuff. There is a fitness value that's being calculated. Okay, and we could go back and see it running. I don't know if they've reached the target yet. I'm going to have to look at like refining and optimizing this example by the time you click on the link in this description. Hopefully it'll work a little better. I don't know if I just got kind of unlucky. I think this one thing might be is the sort of like maximum speed is very low. They seem to be going kind of slowly. so they're not, this one's obviously has the highest fitness of that generation, but this is basically the idea. So what you want to do is think about, use that core genetic algorithm. Again, if I look at the code, last thing I'll just sort of point out here is that you can see here in the draw loop, there are the same sort of set of functions. Calculate the fitness, perform selection, perform reproduction. There's a little bit of a different thing going on here where there's also time. Like in the Shakespeare Monkey example, it's just like every frame, it did a new generation. Now it's sort of counting down, letting these objects live for a little while, then calculate their fitness, and then my brain is like shutting down at the end of this video here. And then like go and then reproduce for the next generation. Let's check on our the flow field, which is it's running very slow, probably because it's got the browser thing kind of going as well. Oh, because I have the debug on. Oh, I left that on. It's probably been running. Let's see, how well are they doing here? Have they made it around all these? No, they're getting stuck at this obstacle. I'm going to let this run for a little longer, and maybe I'll update you somehow through another video of how these obstacles are doing. So I've given you a lot of stuff here. So what you should really do is think about try to build your own scenario. Try to think about what is this idea, how you're going to encode the stuff that's the parameters of your system. How do you express those parameters visually through design or animation? And then how do you calculate a fitness to evolve those parameters over time? And I'm going to do a few more videos to show you a couple more scenarios. A scenario known as interactive selection, as well as a scenario known that I'm calling loosely ecosystem simulation, which I'll get to too. Okay, thanks for watching, and I will see you guys soon in another video, I hope. Thanks very much. Okay, my code is bad, you guys are telling me. I'm going to have to like fix that and come back and make an addendum video, but unfortunately I have to be done for today. Does anybody have any questions you want to ask? I feel like I'm shouting. Am I shouting today? I don't know why. I think one thing is the fan's going. It makes it so I can't really hear myself, and I could easily just talk this quietly at this volume, but whatever. Everyone's yelling at me time. I'm aware. I'm going to shut down in 3 minutes, give myself some time to pack up and leave I have 15 minutes to pack up and leave at 2. I have to look into fixing this particular code example to perform better. I don't know why it's not working so well. And drink the rest of this water, which is running out here. Thank you guys for tuning in today, for bearing with me. I'm kind of closing up shop here. Why do we drive? Kenny asks, why do we drive on parkways and park on driveways? I have one answer for that. This dot's on. What's written on my shirt? People doing strange things with software. This is a processing t-shirt from a few years ago. I'll quickly say that if you have enjoyed this, I guess I usually cover this stuff at the end of the video. I encourage you to subscribe to the channel. Likes and comments and all those things help. One thing I'm excited about is I reached some sort of threshold in YouTube where Google actually contacted me to give me a free channel consultation. So I have some phone call with people at YouTube on Monday. Maybe I'll learn something new. You can become a patron to subscribe to the Slack channel. That's a crowdfunding thing. If you're interested in that, you're of course under no obligation to do this so. And then you can also sign up, put your email address in here to subscribe to updates when I'll do my next live stream. I guess my plan right now is to finish these genetic algorithms tutorials next week sometime. I will be doing a live stream Monday, Tuesday, or Wednesday. I don't know which date yet, and I will announce it on Twitter or here. There is one more week left for the Cotton Bureau t-shirts. Again, I'm not really making money from this. 40 of these have sold. I am actually making $2 per t-shirt, which is nice, I believe. But I'm more just doing it because it's fun and people ask for them, and it's this nice coding rainbow design. That's on the horizon. But this is like kind of one of these things where they get amount of interest and print a certain amount of t-shirts. So if you're interested, I recommend the pink, turquoise, green. I should get the green one to wear in here, clearly. I don't think I ordered a green one for myself, and a purple one. Maybe I'll do that. And then I think that's all of my kind of like logisticsy, businessy stuff to cover. These videos, by the way, won't come out until early next week, the edited versions of them. The live archive will be available also not till next week. I will probably have a preview version of it, an unlisted version of it that I'll share in the Slack channel, or if anybody really desperately wants to review the archive. I don't publish it until it has the kind of like thumbnail and description and links and all of that. And it's going to take probably till Monday or Tuesday to have that done, just because it's late on a Friday right now, and I don't, and Mathieu, who helps me with that, it's it's not going to happen until next week. That's all I'm saying. It's moving, has a lot of stuff going on. I'm busy over the weekend, so it'll happen on Monday or Tuesday. But if you're desperate for it, if because you came late or whatever, just send me a tweet or whatever, or sign up for the Patreon, certainly, that sort of thing. I hope this was helpful. You guys are giving me lots of nice, helpful thumbs up. I'm going to play myself out. This is my going away song. Next week, I hope to have a theme song. Adam Blau, who is a composer in Los Angeles, is composing a theme song. I also shared a kind of draft version of it in the Patreon Slack. Next Thursday, I'm planning on shooting a music video for it. I have a green screen room. I mean, I have a green screen here, but I have a green screen room where I can actually use my entire body. So if you have ideas of things I should do for this music video, I want to order some like costumes and stuff on Amazon. Send me a tweet with that because I need to try to make some orders today to have stuff or by next Thursday. That's why I want to get a rainbow sweater maybe to wear. Sort of thinking reading rainbow. I don't know, that kind of thing. So get in touch about that. Enjoy your weekend. Stay away from the computer if you can. Be outside with your friends and family. Give people hugs. Look for beautiful things in nature. Exercise in whatever way is comfortable to you. Smile at the world. All these nice things, please. Frozen Princess. That's an interesting idea. Not out of the question by any means. I don't know what bullet photography is. I'm looking at Slack messages I'm getting right now, and I'm not getting any tweets right now. I think they would show up on my phone. This song, I think, has got one. Wow, this is a long song for me to play out. Are there 44 people are watching now. Wow, I guess Friday afternoon either isn't a good time or I lost a lot of people with this genetic algorithms topic. Just a reminder, go ahead and feel free to thumbs up various things in the rainbow topics that you're interested in. Submit your suggestions there. It's another thing that I'll mention. Oh, internet hug. How do I do an internet hug again? Let's see if I can. Hold on. I'm in the wrong. Can I hug the camera? Thank you for watching. This is my weird internet hug. Out of focus thing. This has been
Cutting Rainbow.
with me.
Cutting Rainbow.
I hope you all have in your future. Don't forget, when you're doing JavaScript, you need this dot. Okay, that's everything. And now I'm really signing off. Goodbye, and I'm heading out for the rest of my day to see some Scratch programs that some kids have made. Okay, goodbye.